Okay, Africa, are you ready for me to get started with the logistics information?
Yes, sounds great. Thank you.
Okay, okay, perfect. Well, good morning, afternoon, or evening, everybody. This is Jennifer Brennan. I will be your WebEx host for this afternoon's workshop. Welcome to day 2 of the Fundamentals for Using Hyperspectral and Thermal NASA Earth Observation Data workshop. What I'll do first is just kick us off with some logistics and housekeeping information. To ensure the best audio experience, all participants have been placed in silent mode. But if you have any issues or you have any questions, please enter those into the Q&A panel rather than the chat, and you should see this on the right side of your screen. If you don't see the Q&A panel, you can click on the 3 dots at the bottom of your screen to pull up your panel options and then insert a check mark next to the Q&A option. Just a quick word about the chat. Participants will have the capability to chat with the hosts and the presenters, but not with other participants. So if you have any questions, again, please enter them into the Q&A panel so everyone can benefit from those questions. Certainly, if you're having issues with WebEx, feel free to send a private message to me or to Joseph Smith using the chat. Today's session is being recorded. When the recordings are ready, I will follow up with a link to the webbook, which includes, links to all of the presentations that were held both yesterday and for this afternoon session. And I will also send links to yesterday's recording and this afternoon's recording, but that will take a few days. There is some post-processing that's involved with getting those recordings ready for consumption online. We do have multiple speakers for this afternoon's event. We have speakers from NASA's EMIT, ECOSTRESS, and PACE science teams, and also subject matter experts from NASA's Land Processes Distributed Active Archive Center, or LWIR, that are going to guide us through this afternoon's session. It is my pleasure to introduce today's first speakers, Eric Bolsch from LWIR and Emil Sharrington.
I was just going to go back over the slides that I shared yesterday. And afterwards, I noticed a number of participants are in the slides because I had shared a link before. I guess too from the chat, after I go through these slides, while I'm going through the slides, if people could let us know if you've successfully been able to get into Earth Engine per the instructions that were given yesterday. And for those who didn't participate yesterday, this might be new. So the overall thing was, again, we were assuming that some people might already have Earth Engine accounts. And so some of this, maybe you don't necessarily have to do. But for those of you who, when you log into code.earthengine.google.com, and if Africa or somebody wouldn't mind again posting this link into the chat, just in case people, it's hard for them to grab this link. If by chance when you enter, you see this type of window, these instructions will kind of walk you through that. And again, you'll also have access to this afterwards. I don't have access to similar thing to Eric. When you're in presenter mode, you can't see the chat, so I can't easily paste the link to these in the chat. But the bigger thing is, if you don't see this and it's not asking you to register a new project, it's possible that you have already done this process, and so you're good for the part of the workshop where we will be using a toolkit we've set up for PACE. That said, if you did receive this, when you log in, you do see this window. You are going to want to select the top option, which is there in blue and highlighted with that little red box, says, I want to register a new project. And then, as I have indicated in the text on the right, if you are doing this with an institutional account, it's quite likely that you're going to have issues with this. And so our overall recommendation for people is please sign up for the project, because it's a Google Cloud project, and institutional accounts might be limited in being able to create new accounts. So we would recommend, using a personal Gmail account. If you're logging in with a personal Gmail account and you click that blue button, you should come to a window where it allows you to then give a project name And just for the sake of this training, I specified NASA training 2025-07, the year and the month. And you shouldn't need to specify an organization. And after that, you should be able to click that create button to proceed. If the options you see do look different and it's also asking for a location, it's quite likely that you are logging in with an institutional account. That's going to make it difficult or impossible for you to create a cloud project. But again, if you're logging with a personal account, you should see something like this. And do note that it gives you a limitation on how many projects you can create. After you've clicked that create button, you will have to register the project so that you can use it for Earth Engine. You're going to want to hit that register button. And by the way, Africa and colleagues, I do note that I guess from the agenda, Eric and I collectively had 20 minutes for registration issues. And I know that it's already 20 after the hour. Just to say that I'm also fine with relinquishing some of the time for the actual Google Earth Engine or my section of the Google Earth Engine activities. I don't necessarily need to take that full time in case we'll need a little bit of time back. So back to this, just to say again, you're here, you'll need to register your project. And then after you click that register button, you're going to see two options. Because we're doing a training, and again, apologies that if I'm speaking a little fast, because we're doing a training, we should qualify for non-commercial use. So we can click that get started button on the bottom. When we do that, it's going to ask us for multiple pieces of information. One is to select an organization type. Because we're doing a training, we're going to want to select Earth Engine trainer or trainee. Then we can proceed with that next button. And then we're going to check non-commercial eligibility. Since you're the participants, you're going to want to select participant. You're going to want to put in training dates. You can, of course, change the training dates, but I just put in the dates for the training, which were yesterday and today. After that, we're going to click that eligibility button. And based on that, it's going to say you're eligible for non-commercial Earth Engine use. After that, we're going to hit next. It's going to ask us to choose a plan. It's going to indicate, however, that no pricing plan is required for a non-commercial registration. So we're going to hit next. It's going to ask us to describe our work. And as I mentioned yesterday, and if you didn't participate yesterday, as I was saying, the only thing with an asterisk is the question of, will you use Earth Engine for any of the following? So you're going to have to select something there. And as an example, I had picked oceans, ecosystems, and conservation. If that's not appropriate to how you see yourself using it for the training, you can select another option. But the important thing is you pick one of these options and you click OK. You're going to hit next. Then we're going to go to the review summary, which is just giving you the same information you typed in before. If that all looks good, we can hit register. And then a new prompt is going to show up asking you to enable the Earth Engine API. So over on the bottom right where it says enable, we're going to click that. After we do that, you're going to come to a new window where it shows that the project has been created and it indicates that it's registered for non-commercial use. Yesterday, again, I also gave a disclaimer just talking about, as Eric himself had mentioned before, we are platform agnostic, whether we're using Google or Amazon, etc. But for this part of the training, we're going to be using Earth Engine, hence we're using Google Cloud. There are terms of service about how these resources can be used. That said, for this training, we qualify for non-commercial use. So we come to this window and you'll see the name that you have picked. You will need to go back to the other tab where code.earthengine.google.com is located. You might need to refresh it. And when you do, you should come to a window that looks like this that asks you to choose a cloud project for your workspace. In this case, I have multiple projects, but the one that you've created might be called something like NASA Training. So we're going to select that. We're going to click that select button, and then we are ready to use the code editor. Notice that it's not asking us to register a project again because now it's registered. And then the very last part of this, before I turn it back over to Africa, Jennifer, and others, is as I had mentioned before, we had put together this, what we call the PACE OCI Toolkit. There's a GitHub page for this, which has the QR code is there to the GitHub page. just added in, something that's on the GitHub page explaining kind of how we have generated the data sets and gotten them into Earth Engine. And also just to say, acknowledging a whole lot of people who contributed to this work, including people you've heard from before. Yesterday, we heard from Morgan, the PACE applications lead, also Sky Kaplan from the PACE mission team, who was also online yesterday, Fred Humrick, Africa herself, and a number of colleagues of mine from UH and NASA Marshall. That all said, that is one way to get to this repository. Again, because I can't get to the chat, if you were here yesterday, you've already added the repository. If not, we can use a simple link, bit.ly/GEE_repo_PACE_OCI, or you can scan the QR code. When you do that, it will pull up this window here, and it's going to ask you to add the repository to your scripts. You're going to select yes to add it. When you do that, you might not see something immediately. You might need to use that refresh button. And after you do that, you should be able to see a repository called PACE_OCI under your reader scripts. And if we've done that and you now have access to that, then you should be all set up for using Earth Engine for the other exercises. And with that, I will stop sharing. And I don't know if there are any questions about this. I think I was also seeing messages that people are still trying to connect to the hub that Eric and Masa created. But I guess I'll pass the mic back over to Eric, I suppose.
Emil, one of the questions that came up for you is if you could go over project creation again. And then similarly, there was another question about someone got most of the way through your instructions, but the last step eluded them. The project registered, but not sure how to connect the project to the repo.
Okay. Yeah, thank you. Again, I can... I'm not sharing screen. Sorry about that. One moment. Share. Okay. Project creation. I guess just in the event that, you didn't get to the part of creating a project, when you log into code.earthengine.google.com, and thank you, by the way, Aya, when you get here, so you will pick that option of, I want to register a new project. Otherwise, you could click, I'm authorized for an existing project if you already have a project, but I'm just imagining that if you come to this window, it's because you might not have used Earth Engine before and you don't have access to a cloud project. So you're going to click this, I want to register a new project button. It's going to come up with this window, and that's where you're going to have to specify a name for the project, hit create, and then walk through the different steps that I've mentioned. I'm not sure. Well, I hope that kind of addresses the first question about that. And of course, after you walk through that, you can go back into Earth Engine. You can now select that project you created. And then regarding getting the repository that we're going to be using, if somebody would be so kind, Africa or I or someone to, or maybe you already have posted this link in the chat, or if you're viewing online and you just want to scan that QR code, that will add this really long link. It's going to ask you if you want to add this to your scripts panel. You click add, and Diego Inser, a friend of ours from Guatemala, who I see is in the webinar. He was the one way back when in a workshop figured out that sometimes you really have to click that refresh button that you see over here for it to show up. And after you do, it might take a little while for it to fully refresh, but you should then see under your reader section of your scripts, should say user/serverbz/pace_OCI. So I hope that does the trick. Aya, since you were so kind, could you let me know if there's anything else in the chat, or to the person who...
It looked like you got it. And just to clarify for the rest of the folks attending, will these slides be available for folks that would like to follow along on their own speed?
Yes, definitely. And in just a moment, I can share the link in the chat. And then, okay, I just saw, so I'm okay. Once again, how to add the repo. So there are two questions that I saw quickly just pop up and then disappeared. how to add the repo, the easiest thing is bit.ly/ge_repo_pace_OCI. I know it's a long link, but it's a little shorter than this big link here. After I finish sharing this, I will post it in the chat if it's not already posted there. That's how you add the repo, but then it's going to ask you, do you want to add the repository to your workspace? And then you click yes. And again, it might not immediately show up, so you're going to want to refresh. And then you should see it there. So I think that addresses one question. I think one of the other participants said that when they were in the step of, when they were in this step here, that it asks about a location, it doesn't allow them. As I mentioned at the very top, I believe that the people getting the location query, you're not using a personal Gmail. You might be using an institutional, organizational address to log into Earth Engine. And I believe that your organization or institution has restrictions, which then creates the separate prompt. If you do log in with a personal Gmail, this is generally the workflow where it's only asking you for project name and location. You could keep no organization, and then you should be able to create. But again, if it gives you this additional, if it gives you an additional prompt there, I think it's that you have to again use a different account to log in, and I hope that addresses that. I know that we're now at 30 minutes after the hour, so I think I will stop sharing, and I hope that that's addressed most of the questions. But in case anybody, Afka, Jennifer, others have seen other questions that don't seem resolved, please let me know.
Thank you, Emil. Can you share the link to these specific slides in the chat for everyone?
Yes, okay. Just shared those, and then also just Eric and Masa were very kind as well to put the if these are not already linked into in the Vitals notebook, I believe that they will be afterwards. But just shared that. Okay, John indicates you're still not seeing how to add the repo for PACE.
I was just going to ask that question. Thanks, Emil.
Yeah, if you give me just one moment. One moment. Copy. Let me. How do I know? Okay, then I see another question. How do I know if the project is loaded? If I could share the screen just for a moment again, just to try to answer the two questions. We're going to know if the project is, okay, second question. We're going to know if the project is loaded because if the project is fully loaded, when we come in, and I'm sorry, but I kind of blanked out the top here that had the name of the project and whatnot. But if the project is fully loaded, then we should be able to access this window. In fact, let me just pull up, and I think you can still see my screen. Let me just pull up. If a project is fully loaded, you're going to see, the name of your project up here, and then the project is fully loaded. And then, of course, if you have properly loaded the repository, then you should see under Reader, you should see the repository there. I'm thinking those were the two questions that kind of jumped out just now. If not, let me follow up in the chat. And let's see. I think I also saw. I don't know how to pull up the chat here. I saw somebody post in the chat about an error about loading the repository.
Yes, there's actually quite a few messages to that comment. So some folks are receiving error messages. Some are still having trouble understanding where to go to load the repository, and others are not able to load the repository, going through the steps correctly.
I see. All right. If it's just the issue of loading the repository, either by clicking the bit.ly link that I just shared in the chat, which says bit.ly geo repo paste, and you open that, it should automatically pull up. Well, it should automatically in your code editor come up with a prompt that then is asking you. So let me share my screen again. I'm sorry. If you click on that link, you should see a code editor window, which asks you add repository to workspace. If you've clicked add, then we are good. You might still, again, not see the repository load. You might need to click this little refresh button, and it's right next to where it says new, over on the left side. After you click that refresh button, just give it a moment, and you should, after that, see user severe bz/pace _OCI. If you are still having issues, I guess the one thing that I should have mentioned at the very top of all of this, we have sometimes in the past had issues when people are using browsers other than Chrome. It seems to have been resolved recently in terms of Edge. So if you're using Microsoft Edge, I believe it shouldn't be an issue. But if you're using something else like Firefox or DuckDuckGo or another browser, you might be getting an error. And so if possible and you have the Chrome web browser installed, I would recommend that you try these steps with Chrome. And Jennifer or others, could you please let me know if there's still pending issues?
Yeah, that sounds great, Emil. Just in the interest of time, we are going to jump into the next items on the agenda. And please, there are some comments in the chat and in the question and answer window that you can address there. These slides are available so you can follow these steps. Try to use a different browser, but everything should work accordingly once obviously gets up and running. But thank you so much, Emil. So just let me share my screen, and we are going to start with the tutorials now. But before we start working with this data, I just want to have a quick recap on the satellite data sets that we are going to envision. And while I am talking over this, you can also check your environments that are up and running. Once we start running the notebooks, you also have a chance to ensure that everything is properly working, and or you can follow the steps afterwards. So we are going to work with ECOSTRESS level 2 data, land surface temperature, to have an idea of the general characteristics of these data sets. That's why I'm recapping all of this, because you may have heard some of this information yesterday, but I think it's important for all of us to be on the same page of what is the data that we are going to be dealing with today. So for ECOSTRESS, this is the footprint. The general footprint of the image is relatively large with a SWAT of 384 kilometers, but that varies because this is an instrument that is on the International Space Station. So this SWAT is based on the nominal height of 400 kilometers. In terms of a spectral range, these are very long wavelengths, as Glenn mentioned yesterday. So we have 5 spectral bands that cover from the 8 micrometers to 12.5 micrometers range. And the width of the bands varies in between each of them. Then the temporal resolution also varies, but expect a repeat cycle. And by temporal resolution here, we are referring to when do we expect an image on the same place, on the same location. So, for example, with Landsat, we have a repeat cycle of every 12 days so it means that we expect an image every 12 days if we are only working with one mission. And for this, it's about 3-5 days over diurnal cycle. Please note that the instruments that are on the International Space Station are not sun-synchronous. It's following the orbit of the ISS, so the acquisition is different. And the spatial resolution, this is the pixel dimension, is about 70 meters. We have data from 2018 to today. And for the EMIT data, let me close this. This is an instrument that is also on the International Space Station. The images are smaller. We have a SWAT of about 75 kilometers. The spectral range is from the short wavelength to the short infrared part of the spectrum, from 380 to 2500 nanometers. That's the range that it covers, and each band has a bandwidth of about 7.5 nanometers. So these are consecutive measurements. That's why we call them hyperspectral, as compared to the common multispectral measurements that we are used to deal with, for example, those from Landsat, even from ECOSTRESS. This is multispectral. And here we have consecutive measurements that range from 380 nanometers to 2500 nanometers. The temporal resolution is variable because it's an instrument on the ISS. The spatial resolution, the size of the pixel, is about 60 meters, and we have data from August 2022 to the present. For the PACE mission, what we are going to be working with is with the ocean color instrument in this platform. And these are very large images. It have a swath of about 2,700 kilometers, and the spectral range goes from the ultraviolet, about 340 nanometers, to near infrared, 895 nanometers. The bandwidth of each of these measurements is about 5 nanometer, and that's for the hyperspectral measurements, where you have consecutive measurements about every 5 nanometers. And then we have multispectral measurements in the part of the spectrum from 9040 to 2260 nanometers. So just here you can see the difference between the measurements that we get from EMIT as compared from PACE. The temporal resolution is very high. You expect an observation in any given location daily or every 2 days. And the spatial resolution, this is the size of the pixel, is about 1.2 kilometers at nadir. Once you go away from nadir, those are going to be more bigger pixel size. And we have data from April of 2024 to the present. So these are some general characteristics of the datasets that we are going to work with that you may have heard some of it yesterday, but it's good to keep in mind once we start dealing with the data itself. So some highlights from these datasets is that we are using some of the newest NASA measurements for imaging spectroscopy, from the visible to shortwave infrared measurements, and for thermal as well. For thermal, you may have been more acquainted with the Landsat measurements because we do have some thermal bands there, and we can derive land surface temperature. And Glenn explained yesterday some of the difference between Landsat and ECOSTRESS measurements. Then for imaging spectroscopy, I would also like to highlight, because this shouldn't be given for granted, the improved signal-to-noise ratio that we have with PACE and EMIT imaging spectrometers. This is critical when we are working with hyperspectral measurements. I had the opportunity to work with Hyperion many years ago. The signal-to-noise ratio was very bad, so we had very low values. So that meant that the signal was low as compared to the noise, and it was very difficult, almost impossible, to work with the blue-green bands, because we expect a lot of atmospheric interference in those bands. And if you don't have an instrument that is sensitive enough, you will have bad data. On top of it, in the past, the few missions that provide this information didn't provide the surface reflectance measurements, and you needed to calculate it yourself. Imagine calculating the surface reflectance for more than 200 spectral bands for EMIT, and all the pixels is computationally intensive. And the fact that we are already getting the surface reflectance, it means that the atmospheric correction has been applied, and that you can work directly with the spectral signatures of and apply the science more readily. This is a great advance. It makes the data more readily available for application, and is something that shouldn't be given for granted, because we have to deal with this before, do it ourselves, and this requires a high level of expertise on those areas to have very clean data. So I just want to highlight this for the data that we are going to deal today, PACE and EMIT. We are already dealing with surface reflectance, very high quality measurements. In the past, you only had the radiance, and it doesn't show anything of what you would expect for the reflectance of a given element. So there has a lot that has been done already with this data. Then for the thermal as well, we are dealing with level 2 data from specifically land surface temperature. And what we are trying to do with this webinar is to be as sensor agnostic, of course, remaining within NASA, and as cloud agnostic as possible, because we know that for the user perspective, what is important is how do I use this data for my application? And you may not be thinking directly about this mission or this other mission. There are differences in these missions that is mentioned here, but they are complementary, and it's important to learn how to use this data and how even to compare between sensors. Just talking about the spectral resolution of the data that we are dealing with today, I am taking this graph that you may have already seen from Landsat that explains the location of the bands for the different Landsat missions. For those of us that work in land surface processes, Landsat is the holy grail of satellite measurements. So this is the comparison with PACE. We have multispectral measurements for ultraviolet, part of the electromagnetic spectrum, to near infrared. And then we have some multispectral bands in this other part of the electromagnetic spectrum. For EMIT, we have for the 380 nanometers all the way to 2500 nanometers. Consecutive, obviously, there are some gaps in these atmospheric parts where we have too much interference from other particles. And then for ECOSTRESS, this is working directly very long wavelengths in the thermal part of the electromagnetic spectrum. We do have one about 16 nanometers that is used for geolocation. But then the 5 thermal bands are in the thermal part of the electromagnetic spectrum. So I just want to make those clarifications before we start working with the data. And please note that, for example, this graph is only to depict spectral band locations and widths, but it's not at the scale. It's just for all of us to be on the same page of the type of measurements that we are going to be working with today. So that's for it, and we can jump to Aya's presentation to work with the land surface temperature. Okay. Thank you.
Thanks, Africa. Can I share my screen? Let's see. All right, we're actually going to go from the Cloud Workspace setup just to make sure everyone's okay and comfortable with logging in again. Hopefully everyone is already there and all set up, but just in case for folks that need a refresher. And then I know Eric might chime in as well for this part as well. So I'm going to go to click here to start the Jupyter lab. The resource allocation, when it says bring your own image, this is a question that came up. We're going to stick with the Python. We're going to use this resource allocation that's already set up for us of 15 gigabytes of RAM. We'll start this. All right. And now our server is starting up. You'll notice I didn't have to log in because I did log in earlier. In the event it didn't work, sometimes you just have to try re-logging in if you get an error message. Or you can, if you've already done a tutorial like this, sometimes you have to use a different username. So I had to just add a 1 to the end of my username today, and I was able to get in if that happens to you. So Eric, do you want to chime in on next steps for getting set up with our notebooks we're going to use today?
Yeah, sure. So if you're still on the page for the Cloud Workspace setup page, if you scroll down, it shows how to clone the repository, and so there is a link there that you can copy, and then you can just paste that in a terminal. So we can launch a terminal here, and then I'm going to paste it in chat.
Perfect, and I'll grab it from the chat.
So you can just copy that line that I put in the chat, and then put that in there. Yeah. And so that's going to call in the repository.
So
One thing I will mention.
we just put in git clone and then https github.com nasavitals.git.
Yeah, that's correct. And that'll call in the whole repository, and then we'll be able to open the notebooks and start to work with them.
Awesome, thank you. I'm just going to double check and see, can we get some thumbs up from attendees if this is working okay for you? Great, I'm seeing 1, seeing 2. Wonderful. Okay, awesome. Now it looks like this is all done on my side.
You still have a question. Where is terminal 2?
Ah,
How do you get to the terminal? So there's a couple of terminal related questions. If you address those really quickly. Thanks so much, Aya.
yeah. So when you first get in, you're on this launcher page, you'll see your Python notebooks at the top, you'll see console, and then you'll see other. Under the other, you'll just go to terminal, and you can just double click on this. And every time I open up a terminal instance, it has terminal 2, terminal 3, terminal 4. So you'll probably get terminal 1 to start off with. And this is where you would enter in the git clone and the link that Eric put in the chat. All right. Thank you for chiming in on that, Jennifer. So next, I'm going to go over to this vitals folder on the left to open that up. Open, there we go. And then you can see it's still loading in, but we're going to work with the Python folder. Open this up. I think it's just taking a little bit of time to fully set up. Great. Okay. And then Eric, I do want to clarify, are we missing some of the notebooks for the ECOSTRESS one?
Should not be.
Right? They should all be in there. Unless it's just still taking some time to load in.
You can try.
It's in here now.
Yeah.
Okay. So you all might be seeing this where maybe you're only seeing a few notebooks. That's okay. Just try going back, giving it some time. It is pulling a lot of information in, so it will just take some time to get there. I'm going to go back here and just check. Can I get some thumbs up if you are seeing all of these notebooks here? So there's about 9 of them on the left. All right. Seeing some good thumbs. Great. Okay. So we're actually going to start with the Exploring ECOSTRESS L2T _ land surface temperature emissivity notebook today. So we'll just click on it and then it'll start spinning up, as you can see here. All right, so I'm going to get started. If you have questions, well, I'll come back to those once we run through it. Or if there's like a large question, I'll ask one of the other panelists to stop me midway if I need to slow down or anything like that. Noting that, first time you see this, it's going to be a lot of information coming at you. It's okay if you have to come back to it later and go at your own pace and revisit it. Sometimes I have to do that, where first I just kind of have to watch and follow along and then try it on my own, which helps a lot. So we'll get started. This notebook will show how to access Ecosystem Spaceborne Thermal Radiometer Experiment on Space Station, what we're calling ECOSTRESS, data programmatically using the Earth Access Python library, leveraging NASA's Common Metadata Repository, the CMR. This is what Eric talked about at the end of yesterday, if you were able to join us. So we're going to see those things being put into practice today. We're going to be enabling authentication, searching, downloading, and streaming of data with minimal coding. It also shows us how to work with the ECOSTRESS tiled land surface temperature and emissivity product, which is hosted in the cloud, and it's managed by our Land Processes Distributed Active Archive Center, LWIR. The learning objectives for this, so by the end of this tutorial, you should be able to access search the ECOSTRESS data using Earth Access, stream or download ECOSTRESS data, and we'll go into the differences between streaming and downloading. And then we'll also clip the ECOSTRESS data to our region of interest we're going to use. We're going to do the quality filtering for the ECOSTRESS data. And then at the end of this, we'll show how to export the processed ECOSTRESS data. The requirements for this are going to be a NASA Earth Data login account. If you don't have an Earth Data account, you can create one here, and you can click this button and it'll take you to the page to create one. Something to be mindful of, I recognize we probably have lots of different coding abilities in the room. I do ask if you have questions that you try to stay along with us instead of jumping ahead. That way we can just stay on track and perhaps your questions will be answered along the way. All right. So we're going to move on to setting up. So we're going to import our required libraries. We're going to import the following packages you can see here: OS, Earth Axis, NumPy, Rasterio, Rio X-Array, HVplot. So as we go through all of these, we'll just press play up at the top. This will transition us and run the cells that we'd like we ran for folks that are new. So this asterisk tells us that we're busy. That means it's working, it's running, or I should say. And then once it says idle, we know we're good to continue on to the next step. Okay, great, that worked. Now we'll move on to authenticating. This is when we're going to use our Earth Data login through here. So log on to Earth Data using the auth and login functions from the Earth Axis library. The persist equals true argument will create a local .NET RC file if it doesn't exist, or you can add your login info to an existing .NET RC file. If no Earth Data login credentials are found, you'll be prompted for them. So we'll go here, we'll press play. All right, now here's the fun part. Let's make sure I have my username. So I'll put these in. And I encourage you all to do the same if you're with me at this step. All right, and then I just press enter. Am I having some issues? That's good. Saying busy. So this part can take a lot of time, especially if we have lots of folks doing it all at the same time with us. So we'll just let this run.
Did it ask you for your password here, Aya?
It didn't. It just asked me for my email, and then I gave it my email. Should I try refreshing it? It usually asks me for my password, but I don't know.
Yeah. Maybe comment out that print line and try it again.
Coming out this one.
Yeah.
Let's see. Busy. All right. I'm going to just click back, even if I'm having some technical difficulties with my computer. I'm going to see, can I get thumbs up if you were able to successfully put in your email and password? Okay. All right, lots of thumbs up. Great. I'm going to try refreshing the page, and then ideally that should work.
Yeah, you might need to restart the kernel and just run those two cells again.
So I just want to put this out there. I know we're a bit behind time, but there have been several participants who've noted that because of some of these issues, loading the repo and so forth, it would be helpful to slow down a little bit because some of our participants are having a really hard time keeping up with where you are right now.
Okay, thank you for that. Yep, we'll definitely. I can also take a couple steps back while I allow the kernel to readjust. I just restarted it. So I'm going to go back. So just to clarify, we did the terminal, we did our git clone, and then the link that Eric had posted in the chat. And then that put the repo in, and we should have vitals on the left-hand corner here. If you click the vitals, we then have our Python folder. And from the Python folder, we are now in the Exploring ECOSTRESS notebook that we opened up here. And reviewing, this is what we're working on. Here are our learning objectives, our requirements, setup. I'm going to run the setup cell, making sure it's working. Okay. And now we're going to try our Earth Access login again. Great. All right, now it's working for me. Thanks for that feedback. So I'm going to put my Earth Data login username in there, and then it auto-filled the password that I have. Oh, but the credentials have changed, likely because I've done this before. One moment.
Just add a clarifying note here. So you need to enter your Earth Data login username and password. If you did not enter the username as your email, like you didn't enter the email as your username, so you need to use whatever you use while creating an account. So in this case, Arya is using email, but that's really the username that you used while creating an account.
Correct. Okay. So I should be all logged in. Now it just ran it and worked. Also, make me do it again. Next, we're going to move on to searching for ECOSTRESS data. In this example, we will use the cloud-hosted ECOSTRESS land surface temperature emissivity level 2 product, but the searching process can be used with other things such as EMIT or ECOSTRESS products, other collections, or different data providers, as well as across multiple catalogs with some modification. The land surface temperature and emissivity values from ECOSTRESS level 2 tiled land surface temperature are derived from 5 thermal infrared bands using a physics-based temperature and emissivity separation algorithm, TESS. If you were with us yesterday and you heard Glenn talking about the algorithm, the TESS algorithm he was using, this is that. So you'll also get to see that in practice today as well. This tiled data product uses a modified version of the MGRS, Military Grid Reference System, which divides UTM zones, Universal Transverse Mercator Zones, into square tiles that are 109.8 kilometers by 109.8 kilometers with a 70-meter spatial resolution. So we're going to start by defining our query parameters. We can search for granules using attributes such as collection short name, collection ID, acquisition time, and spatial footprint. For this exercise, we're actually going to work with Boulder, Colorado. Boulder, Colorado gives us a really good example of different land surface areas, such as water bodies, urban areas, and even foothills and agricultural, where you can really see the different temperatures across the landscape. So this is where we're going to look at today. We're going to define our coordinates for our bounding box. We'll create a print statement for it, and then we'll create a simple polygon that'll show our study area for the visualization as we work through this. To do that, we'll do bounding box _ geometry, our study area, create our geodata frame. We'll name our study area Boulder, Colorado, and then we'll set up using HVplot how to visualize our study area. For this, we'll press play. Note that if you wanted to apply this to your area of interest, what you could do is you would just get your own coordinates for your area, change some of these variables around to make sure that they match the name. So you wouldn't use Boulder, Colorado, you'd use Los Angeles, California, or Puerto Rico, and you would change those things around. So this is really helpful code to move it around if you are at that level of skill. Otherwise, just follow along with us as we go through Boulder, Colorado. You can see here what it does is it gives us our plot. You can already see that we have some of the foothills here on the west. We have our urban area in the center. You can start to see some water bodies along to the east and north side of this. So these will be really interesting as we look at the thermal data. Below, the parameters include provider, short name, version, bounding box, temporal, and count, which we are using for our query. Next, we'll get the downloadable links for land surface temperature and the quality layers using data links method from Earth Access. So here we'll run this to search for data using this bounding box and with our Earth Access. So you can see here our provider is LP Cloud, the short name eco_L2T_LSTE, version 2, bounding box, B-box, temporal. So our temporal, our dates for this are going to be the summer, July 1st through August 1st of 2023. This is going to give us a great window for looking into those summer heat days if you're looking into urban resilience applications of using ECOSTRESS. And now we'll run that cell. Next, we're going to move on to getting the downloadable links for LSTE, quality, and cloud layers using the data links method from Earth Access. For this data, we want to make sure that we have all 3 of these layers. So first, we're going to use get links for the land surface temperature. It'll print the first 5 of these links here. That's great. That means it works. That's what we want to see. Next, we'll do the same for the quality. With the QC links here, we've got the first 5. Perfect. And then we'll move on to our cloud layer. All right, got the same 5 again. Let's take a look at the ECOSTRESS tiled data file name. So you can see here, we have our file name, our sensor, product version 2, processing level and type, tile, our geophysical parameter, our orbit number, our scene ID, NGRS, date of acquisition, time of acquisition. A note on the time of acquisition, you can see that this was around 8:14 in the morning. Let's keep that in mind once we get our visualization so we can also help put that into context as well. We also have our date of acquisition. This is right in between our temporal time frame, which is great. And then we have our product iteration number, our build ID of software that generated the product, the layer and band name, LST, just what we wanted. And then we need to know that it is a TIFF file. So that's our data format for this. Looking at the military grid reference system, MGRS tile ID of outputs, they're all in the UTM zone 13, which might be something else that we need to keep in mind. I'm going to come back and can I get some thumbs up to make sure that we have folks following along and are doing okay? Great. Thank you. For the next section, we're going to look into how to access the ECOSTRESS L2T land surface temperature. The ECOSTRESS data is stored in NASA's Earth Data Cloud and can be accessed in 2 different ways. You have the downloading and then you have the streaming. Downloading, you can think of it as more of the traditional sense of working with the data. This has been a supported option since the inception of the NASA DAACs. Users can use the data links to download files to their local working environment. This method works in both cloud and non-cloud environments. For this exercise, we're going to look into streaming. So streaming offers a way for folks to work with the data without having to download. So if you have limited storage space, the streaming access can be really, really helpful. The streaming enables the on-the-fly reading of remote files, so files not saved locally. However, the access data must fit into the workspace memory. So if you remember what Eric was mentioning earlier, so we're looking down here at the bottom of the screen, we can see mem, and you can see we have plenty of memory to work with this notebook moving forward, but this is where you would look for your memory. A note, streaming data is stored in the cloud without downloading is called in-place access or direct S3 access. This is only available when working in a cloud environment deployed in the Amazon Web Services, AWS, US West 2 region. The Python libraries used to access COG files in Earth Data Cloud leverage GDAL's virtual file systems. Whether you're running this code in the cloud or in a local workspace, GDAL configurations must be set in order to successfully access the ECOSTRESS COG files. For this exercise, we are going to open up a context manager for the notebook. I lost my spot. for the notebook using the rasterio.mv model to store these configurations. The context manager sends this information, including an authentication token or cookie when connecting to a file, and can also customize how the file is handled locally. A list of all the configuration options can be found in the GDAL configuration options documentation. While the context manager is open, we will be able to run the open or get data commands that would typically be executed with a with statement. Entering the context manager for multiple cells of the notebooks allows us to more freely interact with the data. We'll close the context manager using the MV exit, where we have all the data loaded into memory. In this example, we will show how to stream the data. For that, the GDAL configuration is set, and the one of our LSTE files is read into the workspace using Open Rasterio from the Rio X-ray library. Since the file consists of only one layer, we can squeeze it, removing the band dimension. All right, so let's put that into practice. We have here our Rio_env equals. We're going to do this. We're going to set up our enter function and play. Great, that worked. And next we'll do the band squeezing. Okay, and now with our outputs, we can see what we have. Xarray.data array, you can see our data array, coordinates, indices, attributes as well. As mentioned, the ECOSTRESS product we are using here is tiled, and the CRS is dependent on UTM zone. For this tile, we can look at the spatial reference variable through the interactive object above to see details such as WKT, well-known text, representation of the CRS, and other attributes. We are using hvplot for visualization here. For detailed information on available open source Python tools and library for data visualization, see this, the pyviz.org. Now we're going to plot the data using hvplot reproject function. It's applied only for the visualization to make sure to specify the CRS, coordinate reference system argument, within the hvplot.image function, so the S3 imagery RBG background tile aligns with our scene. So that's what we will do here. We have size offs, set it up, and then we'll do our reprojecting onto the EPSG hvplot image here. Okay, great. And now we have this wonderful, beautiful scene here, and you can see the range of colors showing our range of temperatures as well. It's in Kelvin. This is something we'll look into a little bit later, but what you'll see here is you have the colder mountaintops to the west, and then to the east, you see as we get to the plains, it's a little bit warmer. You even start to see in this bottom corner, you can really see those streets in the Denver area lighting up as being hotter as well. So our study region is still just a little bit of this scene. So for our research, if we're focusing on Boulder, we want to really zoom into this area. And we want to just focus on the data for there so we don't have to work with all of this. This is still really helpful for just showing the temperature variations over space and all of the data that we can get with ECOSTRESS. So in order to focus on our bounding box, we're going to crop it. So we're going to move on to this cropping ECOSTRESS data. We'll use a clip function from Rasterio, which is used to mask data outside of our region of interest. Before clipping, we need to reproject our region of interest to the projection of our data set, which is UTM zone 13 north. I'm going to pause again. Can I get some thumbs up to make sure everyone has a map of a visualization of the ECOSTRESS data? Great. Thank you all so much. All right. Moving on to the cropping. We'll run this first block to get our study area. All right. There's our polygon. Awesome. And now we'll use the Rio and CRS. Okay, there we have it. We'll reproject our polygon. Run that. Great. And here you can see some of those specifications that we added before. Now we're going to do the clipping for our region of interest here. Great. And now we'll move on to plotting it. So let's see our clipped scene. We will also want to do this for our quality layer as well. Here you'll see our clipped scene. You can really see that pixel size coming in, but what you start to notice is the area. So what you can see here, and if you remember when we talked about this earlier, this scene was from about 8 a.m. So what you're noticing is these really light yellow to the west, and that's actually the foothills. So if we know the sun rises in the east, you can see it being warmed up compared to the surrounding area by the sun. And then you also start to see in this dark purple here, you start to see some water bodies. So pretty fun way to take a look at this. And then you even see the city of Boulder starting to light up here. Next, we will repeat the same process for our quality layer. So here we're going to use open rasteria. We're going to do our band squeezing. We'll clip it, and then we'll do an HV plot as well for that. Okay, we can ignore this warning for now. And then here you'll start to see the difference between quality layer and how that presents as it's cropped. And now we're going to want to move on to some quality filtering. The quality values are 16-digit bit values, with bits 0 and 1 being the mandatory QA flag that we will be interpreted as. So if you're getting 00, that pixel's produced in its best quality. That's what we love to see. 01, pixel produced, nominal quality. Either one or more of the following conditions are met. So you either have emissivity in both bands, 4 and 5, which is less than 95%, i.e. possible cloud contamination, or 2, low transmissivity due to high water vapor loading. For that, you'll want to check the PWV values and error estimates. 3, pixels fall on missing scan lines in bands 1 and 5, filled using spatial neural net. So you'll want to check your error estimates. Recommended more detailed analysis of other QC information. 10 equals pixel produced, but the cloud is detected. And then 11 equals pixel not produced due to missing or bad data. Users should check data quality flag bits. The detailed quality information is provided in Table 3 to 5 in ECOSTRESS product specification document. So below, the unique quality values are extracted from our CLIT data, and only the values showing good quality is kept. So we'll run this here. Okay, and there's our good quality. .WIR method is used to filter the quality and keep only the LSTE values generated with the best quality. So we'll add that and add that to our ROI mask here, which you can see again, as might look familiar from what we did above. One important note is there is a known data issue related to quality of EcoStress Tile LSTE version 2 data. All users of EcoStress Level 2 version 2 products should be aware that the cloud mask information previously available in the quality control layer in version 1 is not available in the version 2 quality layer. Instead, users should be using the cloud mask layer in Level 2 LSTE product or the cloud information in the standard cloud mask products to assess if a pixel is clear or cloudy. Note, we've added the cloud layer above, so we are good on this front. To learn more at the product CMR page to identify clear pixels, you must now apply an extra filtering step. In the cloud mask layer, value 0 means absence of cloud, and 1 means presence of cloud. When processing, ensure you retain only pixels with a value of 0 in the cloud mask layer to exclude cloudy pixels. So for that, we will do this here. Run this. We get an error. It's okay. We can keep moving. And we'll do this again to show the WIR function. And then we will plot our image. Okay, so here we have it with our quality masks and cloud filters. But what you're seeing is the striping that's happening here. This is likely an instrument artifact, but what you look and see down below is you see some more masking, which is likely due to clouds in the southwest corner of this, in the southern portion of this. But for now, we have this. So from this point, we're going to actually work on interactive map exploration. So if you were using this for research or you wanted to have specific, of course, you can just move this around and you can see, moving your cursor on the map, the values in Kelvin. But if you were interested in having a little bit more of an interactive feature and changing it from Kelvin, Celsius, Fahrenheit, that's available. So that's what we will do with this code block here. It's pretty thick, so feel free to just press run and it will go. What we'll do here is create simple thermal explorer. We'll use our base data using the already filtered with the masks eco_LST_ROI_mask data. And then we'll convert the land surface temperature data based on selected unit. We'll create our plot settings using your size ops, and then create the main plot using geo equals true for proper projection. We'll have a statistics panel on the right, calculate stats on valid non-NaN data only, our interactive functions, layout, etc. So for this, we'll press play. Okay, and there we have it. So I'm going to switch this to working in Fahrenheit. So for that, we can just click there, and then we'll get our values in Fahrenheit. So you can see here the mountains, the foothills on the west that are lit up are about 75 degrees compared to these water bodies here in the darker purple, which are 64. You can see on the right the temperature statistics. So our minimum is 58 degrees, which is likely in this bottom corner here. And then our maximum is 79, which I believe came up on the foothills. But even if we wanted to zoom in, which is available on these features on the right, we can use this, and let's zoom into our urban area. So for this, what I would probably do if I was using this for any kind of analysis deeper, I would probably try to find a different scene that didn't have the striping across the urban area. For this example, it's fine. It's actually a good thing to clarify and talk about. So here you can still see that the urban area is lighter than the surrounding area. And you can get specifics with the translucent nature of the scene. You can see how different areas with more urbanization have warmer temperatures compared to areas like this that are water bodies that are cooler. And as you zoom out, you see this as well. Here, you can see the areas near the streets are actually warmer than the fields. So this is a fun thing to play around with. I know we're short on time, so I won't spend too much time investigating this. Although as a geographer, I can easily nerd out about all the little nuances we can see within this area. On the next step, we're going to do the writing outputs. So we'll save our work, essentially. So we now have our ECOSTRESS scene that is clipped to our ROI with only good quality values. Finally, we can save this file locally. Here we go. All right, and so we ran this here to save it, and we've got it. And again, big thank you to LWIR for putting this notebook together and for your support. If you have any questions for them about this, you can look at other notebooks or use their information here to contact them. All right, thank you all. And what I will do is I will answer, since we're short on time, I will just answer questions in the chat and the Q&A, so other folks can move on if they need to.
All right. Well, thank you so much. I really appreciate that. So let's see. We are up next for, I guess we're moving on to the EMIT fundamentals with, is that right, everybody? Eric, Masa, and Aya.
Yeah, that's all right.
All right, Eric, I'll toss it over to you. Thank you, everybody.
Okay. So I'm gonna pick up here just sort of after we've cloned things, except we're gonna work on a different notebook.
Sorry for cutting you, Eric. Could you please make your screen bigger? There's somebody in the chat asking us to have a bigger screen size. Thank you.
Yep.
Just as a quick add-on to that, I did see that that note, there should be an option for each individual participant to zoom in a bit as well with the plus sign just above where you're viewing Eric's screen. So hopefully you can see that as well if you need further magnification. All right, thanks so much.
All right. So the first thing we want to do, like we previously mentioned, some of these notebooks take a lot of memory, and this is the main one that will take a lot of memory. So the first thing we want to do here is on this toolbar here on the left, you can look at your running kernels. And if you previously have been running Aya's notebook here, it should show up right here. And there should be an X, or you could just click shut down all. Please shut that down, and that'll just prevent the notebook from crashing midway through if you run out of memory. So back here, we can see that in this directory, we have these notebooks. We're just going to do this exploring EMIT L2A Reflectance notebook. And so you can just double click to open that. And then if you click on this toolbar on the left, you can collapse this. I'm just going to do that to help everybody visualize this a little bit better. And so in this notebook here today, we're just going to open an EMIT scene, and then we're going to ortho-rectify it, and then we're going to look at some spectra. And so this just has a little bit of background. I'm not really going to talk about that right now. We'll just go ahead and kind of get into the notebook since we're a little bit behind. So the first cell here, we're just going to import the required libraries. And here I will note that this repository that everybody cloned, it includes a module called EMIT Tools, and that has some nice handy functions for working with EMIT data that we'll leverage later in the notebook. So we're going to import those here as our last step of the import process. If you already authenticated, like you ran the previous notebook, when you run this, it should just run, and then you'll be signed in and ready to load the NASA data. If you didn't, just take a second and sign in with your NASA Earth data account. I know maybe that was probably with this said things a little confusingly. So like that it was separate from the login information for the Jupyter Hub. But if you just use your Earth data account to sign in here on this line when prompted, that should work for you. And so I'm going to spend a little bit more time on some of the searching that you can do. And so the first thing I'm going to do is actually search for all the EMIT collections. And so there's a search datasets function that's part of this Earth Access library. The Earth Access library is a great Python library that you can use to search all of the NASA Earth science data in that CMR, Common Metadata Repository that I mentioned yesterday. So here, when we run this cell, we'll basically be retrieving all the collections that have this EMIT keyword in it. And so here you can see that there's 19. And here we can actually print that out, and this will just print like a JSON dictionary that you can look at. But we can also kind of just pull out information we want. So really what's helpful when you're searching for these data sets are things that the short name, the concept ID, the version, and the entry title, which is sort of a description of the data product. And so we can pull that information out of this collections list and just print it as a data frame. And so that's really handy. We can see like the short name, like what it is over here on the right. And then this collection concept ID, which is a unique ID that we can use to search for data sets. Typically, you can either use the short name or the collection ID to search, or collection concept ID to search. Occasionally, there are data sets that have the exact same short name, especially some new like test data sets and things. So typically, like it's best practice to search by this concept ID, although that's not what we do here in the notebook. So of course, breaking my own rules. Anyway, these are some pieces of information that can help you find what data set you want to search for scenes from, and then work with that. So one thing quickly is we can just copy this right here, and we'll use that later to search for a granule. And a granule or a scene, that's essentially the same thing. And it's just a single, like, sort of spatiotemporal, like, scene, essentially. And here I provided this table. This is sort of all the search parameters that you can use with this with this search data function that we'll use down below. The first thing we want to do is provide some spatial constraints. And so we just are going to create a bounding box tuple of the region we want to search for. And this is just like upper left and, lower left and upper right coordinates here. So you can just define that. And then here we'll actually do our search. And so we've got that short name that we retrieved from the table above. We've got our bounding box that we just provided up here. And then we can also add like a temporal range. And so here we're just doing from June to the end of September 2023. And then one last parameter we can also provide is cloud cover. And so cloud cover is not always a metadata field that's searchable. Not every single data set has this, but EMIT and PACE do. So when you're searching for data for those two instruments, you can provide this cloud cover argument. And so we can go ahead and search for results. There's not a lot of scenes here. A lot of these are being filtered out by the cloud cover argument. But also, because the revisit time is sort of unusual with EMIT being on the ISS, there's not like a standard amount of scenes that you're guaranteed to have for any area. And so we can print like one of these results, and you can see that it's basically a dictionary with all kinds of information in it. And we can write some code, we can use this function that's built into Earth Access that helps you retrieve the links. In this example, we're going to retrieve HTTPS links. And this is to keep this notebook cloud agnostic. So it'll work if you run it locally, if you're in the AWS cloud, or if you're in another cloud environment. Here, instead of external, you can also provide direct as an argument, and that'll give you the S3 links if you are working in the cloud and want to use those. So this is returning a nested list. And so within this list, there's a list for each granule and every asset included. And this is kind of confusing to work with initially. So we're going to do, we're basically going to flatten this. So now it's just a flat list. And maybe that's a little easier to see if I zoom out just for a second here. Here you've got like, this is a granule, and there's three different assets. There's a reflectance, the reflectance uncertainty, and the mask. And so actually today we'll use the reflectance and the mask in this workbook. But here we've just flattened that to make this easier to work with. So getting started kind of working with the data, there's two sort of options here. You can either download the data or you can stream the data. Typically with newer data sets like EMIT, we recommend streaming. This is a little difficult for hyperspectral data like EMIT because the files are so large. But it does work pretty well if you're in a cloud environment because there's not a lot of latency. This couple cells here just shows how you could download these scenes easily if you want to use that approach. But here in this notebook, we're actually just going to stream the data. So what you can do here, we want to just grab a URL for reflectance and a URL for the mask layer. And we'll just name these right here. And so before I mentioned, having to authenticate and use Earth Data Login. So to kind of do the searching and things like that, you don't actually need to sign in, but to access the files, you do. And so here, what we're going to do is we're going to launch an FS spec session. And what this does is it takes the URL and it tells Python how to manage it. And so basically, anytime we touch this file at the URL, it's going to go ahead and provide our login credentials. And so we can open that. And now we have basically like a file path we can provide. And then I'm going to go ahead and run this cell. And this is just using the EMIT xarray function, which essentially is going to open the file and all of the groups. So go ahead and run this, and I'll explain a little bit. So the EMIT data is distributed as a hierarchical netcdf file. And so that means it has a couple different groups. And so there's a root group, which is basically like the reflectance data. And that's in down track and cross track coordinates, which is going to be your sort of instrument, which are those of your instrument. And so it also includes a sensor band parameters group, which is going to have like your wavelength information. So you'll have all your wavelengths, and then also your full width half maximum for each band. And then lastly, there's a location group. And so the location group contains the latitude and longitude values for the center of each pixel described by the cross-track and down-track dimensions. But then it also has a geometry lookup table, which can be used to ortho-correct the scene and put it on a geographic grid. And that's built into every EMIT scene, so people can kind of regrid it the way they would like, or maybe not the way they would like, but consistently, excuse me. So they can regrid it consistently across scenes. And so here we can see, this did take a little while to load because the EMIT files are about like 1.5 gigabytes. But we've now got this open as an X-array data set. You can see that we have the down track and cross track coordinates, and also the wavelength as coordinates, and as well as all these other things. But these are the primary dimensions that the reflectance is working with. And then we can use these other things to give us more information about the file. So here, what we can do with this is we can do something like use the select function from X-array to pick out a wavelength we're interested in. So here what we're going to do, we're just going to grab the wavelength, every pixel from the scene that's at 850 nanometers, and then we're just going to go ahead and visualize that. So this is going to give us a good idea of what the scene looks like in the raw instrument down track and cross track coordinates. So you can see here that this is at 850 nanometers. We've got like a mountain range kind of here in the middle, and this is near Boulder, Colorado. So we would actually expect, this is going to run sort of south to north, the Rocky Mountain range. So you can see that it's not north up like a normal image. And so to kind of work with this data, we'll have to ortho-rectify it. So that's kind of going to be our next step here. And so this ortho-XR function is going to apply the GLT to the data and put it on a geographic grid for us. One thing I'll go ahead and mention here while this is running is that during this ortho-rectification process, since we're basically going to, part of what we're doing is rotating the image, we're going to introduce some fill values. And the function that we used up above is going to set those to -9999. So to visualize this a little better, we want to replace that with not a number. And at the same time as we do that, we can actually take this good wavelengths coordinate layer here. And what this is just an indication of whether the data is good for that wavelength. And what this consists of is areas that are where water absorption features are occurring are assigned a negative value in the reflectance during the atmospheric correction. And so we're just going to go ahead and mask those out as well when we assign some values to not a number. So we're going to block out the water absorption regions and then also the areas that are outside the scene after we ortho-rectified. And so sort of after we apply that step, what we could do is plot this again with latitude and longitude as our X and Y dimensions instead of the down track and cross track. Here, before we do that, we'll do this same step to just grab the band at 850 nanometers. This is taking a little bit of time. There we go. So here you can see on a base map, like we've got this the scene, and you can see the mountain range here, and the water body off to the side, and you can kind of see a little bit of the city urban area over here. So this is kind of how you can put this on a map that allows you to work with the data. And now we can do some stuff like plot spectra as well. Since now that we're working in, since we're now working in latitude and longitude, here what I'm going to do is just retrieve the same center. So we can just kind of find the middle of the latitude values and the middle of the longitude values, and pull those numbers out. And then what we can do is we can actually retrieve the spectra from those points using the select function for the latitude and longitude. And so this will give us a spectral plot of a point near the center of the scene. So in this plot, you can see where did this point come from, but also you can see these areas here that are empty, and this is where we mask out those water absorption regions. And so the next step here, there are quality data. We had the mask file. So here again, we can use this EMIT X-array function just to load the mask data. This time, we're going to go ahead and ortho rectify it, and that's a flag or argument you can add in this function, and it'll go ahead and do that for you. One thing I will mention is that it is more memory efficient to go ahead and apply the mask before you ortho rectify, but we didn't do that here. This is just kind of an example to kind of show like the processes you would work through. And we wanted to look at some actual imagery first before we went and started masking things. And this can take a little while since it's loading a pretty big file. So here we've got a mask file, and you can see that it's ortho-rectified or on a grid, so it's in latitude and longitude. We have these 8 mask bands here, and those have things like clouds, cloud mask, water mask, things like that. So I'm having trouble like scrolling here. It wants to go too far. But if we run this cell at the top, that is just going to show and list all of those bands. And so you can see cloud flag, cirrus flag, water flag, dilated cloud flag, spacecraft flag. And then there's 2 that aren't flags, and that's the aerosol optical depth and the water content. But we're just going to work with the dilated cloud flag here today. So the dilated cloud flag is basically inclusive of the cloud, the cirrus, and it's just a range around those pixels where there's potentially clouds. And so we want to omit those from our sort of analysis. So what we can do, we can select that band, the dilated cloud flag, and then within our data, we can apply, we want to mask out these fill values again as not a number, and that's just for visualization purposes. So we could do that, and then we can visualize our cloud masks. And so here we're going to change up a little bit about the way we're plotting. You can, since we plotted a lot of things, we just want to create like a common dictionary to sort of help us build those plots more easily. So we can just provide these kind of separate options that we'll use in HV plot. And then we can unpack those as we apply this, and it'll just add all of these consistently for the next couple of graphs we make. And this is slowing down a little bit. I think that's probably because we have so many people running this right now. But this will provide us with a similar plot to what we had before. It's just going to show that layer. Here you can see all the good data is here at 0 in purple. and then ones indicate the area we want to mask out, where there's potentially clouds. You can see these little dilated dots. And so what we do is we can apply, or we can we can change those values in the reflectance data to not a number based on where this mask is 1. And so we can go ahead and do that. And then we can plot our single layer at 850 nanometers again with these regions masked out. So just to kind of keep the pace going while this is loaded, I'll go ahead and talk a little bit about the next plot. So in the next section, what we're going to do is we're going to make an interactive plot. Here we go. So here you can see, we've masked out these regions. And you can see that applying that mask worked properly. So the interactive plots, a lot of times when you're working with imaging spectroscopy or hyperspectral data, it's very helpful to have like an RGB image, to be able to hover over the scene and retrieve the spectra at different locations. It really helps like identify things and kind of understand what's happening. So here what we're going to do is we're going to create an RGB scene. And how we'll do that is we'll take the reflectance bands closest to these wavelengths here, 650, 560, and 470. And then we'll apply a small gamma adjustment just to brighten it so it's a little easier to look at. And after that, we can run this sort of interactive cell down here below. And I can quickly kind of explain what it does while we wait. So it is complicated. It's a lot of code to look at. But essentially here, we're starting with the scene center. And we're going to set a limit of 10 points. So you'll be able to click on 10 points on the map and have the spectra returned at those locations. And so we just kind of define an initial point, and then we build this streams object that we're going to connect with our plots. And then we add a RGB plot, and then we connect these streams with where your mouse is hovering or tapping. And so it's going to create a really cool scene here, or image. So we can run that cell. And after we get this up here, we'll be able to sort of interact and check out the spectra at different locations. All right, so here, pretty cool. We've got like our center pixel that we have, and then we've got our RGB scene on the right, and then here we can click in this scene, and it'll add these markers, and then they will show up, maybe, on the left here. Oh, I'm curious why that's not working now. Maybe I'll try running it again. It could be that because we have so many users online, that the streaming feature is not working. And I see a message. Someone said it's very slow, but can confirm it does work. And that's probably just the limited resources. There might be a lot of people on the node that I'm on running this that's limiting the speed here. But I think if it's working for other people, I'll just go ahead and move on. And I can show here. We have an image at the top of this that shows what it looks like, just in case this isn't working for other people. You can add points, and it'll look something like this here. So you'll be able to have these nice stuff. Yeah. You can compare them. You can click and drag the points around to see the different things. I'll give it one more shot, but it doesn't look like it's going to work for me. Anyway, so after you've selected like 10 spectra or something like that, you can actually extract the data here. You can run these next two cells, and what they'll do is they'll pull that data into a dictionary, and then you can write it as a CSV. So you'll have like a CSV file with your spectra at the selected points that you want. And, that includes like longitude, latitude, the wavelengths, and then the reflectance at each point. And just again to reiterate, this should work faster if you have more resources. I suspect right now we have about 300 people on this hub, and that limits like users to about I think it was like 1.5 CPUs or something like that. And that's probably just too little to make this figure work. But with that, I'll go ahead and end this notebook, and we can move on to the next section. I think we're still a little behind.
All right. Thank you, Eric. Oh,
Sorry for cringing. Eric, would you be able to show how to shut down the hub for people that are having issues that is not being resolved? Maybe try to shut down your hub and again start your server, so that might resolve the issue. Some people are not seeing the notebooks there. If you cloned it properly, maybe there is an issue in the hub or the memory issue. So try to shut it down and try again.
Okay, yeah, sure. Just quickly to show how to do that. You can go here to File, and then scroll down to the bottom to Hub Control Panel. And this will allow you to stop your server and start a new one. So like after you stop it, you can click Start My Server, and it'll launch a new one. And you can try again with the clone and everything. And it'll let you reselect this again. And it should start back up, and you can be back at the beginning, starting from scratch. Or if you've already cloned everything, it should remain in there if you're still signed into your same instance. Do you think that covers what you were talking about, Masa?
Yes, and another thing is that if you can you show the CSV file that you stored, including the spectra?
I'm having an issue understanding Eric's audio. I'm not sure if other participants are experiencing that.
Yes.
Eric, your audio's not coming in very clearly. Maybe you'll need to, I'm not sure, maybe log off and log back in and see if that works. Or we can try it again and see.
What about now? Is that better?
Yes, that's better.
Okay.
Is that better for everyone else?
Sorry, I had to switch microphones. I've been having some hardware issues. So back to what I was saying, I think when I ran into audio issue was about the CSV file. I didn't actually export it, so unfortunately, I can't show that. Maybe if somebody else that's a panelist was following along, if they'd like to share their screen. Otherwise, sorry.
No, just I can share it if that works. Let's see. Here. So you can see my screen.
Yes, we can.
Okay, great. So this save it in the data folder. So you can navigate here to vitals data, and the name is EMIT click data CSV. So there are previous files here, but it should be here. It's here. And we click data CSV, and you can download it from there. And then you can use that spectra to train your model, machine learning model, or other to create different products. I just also, I'm downloading it. I don't want to.
I will say,
Yeah.
sorry to interrupt you. I forgot. If you double click it, it'll actually open in the Jupyter Hub, so people can see it.
Nice. And I just want to say that this spectra is so clean and beautiful. It's very, very high quality product. Just want to highlight that. Thank you so much, Eric.
Yeah, thanks for that.
Okay. So if we check, maybe we won't take a break and we just continue with the tutorials if that works for everyone. So we stay on top of everything. I'm going to share my screen. Let me see here. The next tutorial is going to be working with PACE data. So I'm going to share. Let me go to the folder that has all the tutorials. I have already turned off the kernel for this one. I'm going to close this. And the next tutorial we are going to work with is the exploring PACE OCI data.
Africa, could you copy and paste the Jupyter Notebook link into the chat? That would be wonderful. I really appreciate that so much.
Oh, thank you, Masa. Masa did it. Yeah, it's kind of hard to see here the chat, but thank you. So, and by the way, we are not going to go through all the tutorials here, but you can explore these at your own pace and time. No pun intended with the PACE data platform. But there is another very nice tutorial to find coincident EMIT and ECOSTRESS datasets. So now jumping to the PACE, the tutorial. We are going to work with the level 2 surface reflectance data. I encourage you to visit the algorithm theoretical basis. If you click here, it's going to open the link for that specific algorithm theoretical basis data product. And it has a lot of documentation about how that data product was created. Let me shut out this kernel. I don't know what is showing. So what we are going to do here is to explore the level 2 surface reflectance data from PACE OCI instrument over land. Please note that if you are working over the ocean or water bodies, you may need to use a different data product because this webinar is a lot more for terrestrial ecosystems. We are going to work with the surface reflectance data. Overland data product. So we are going to search and access some specific granule based on date and location, explore the data structure, and plot individual spectra, save that spectra, and create some unique hyperspectral enabled vegetation indices. So first, you may need to run this line to install this library because it's not available currently in this hub. And once you click on a cell and run that code, this indicates that it's still running. You can also see it over here when it's running. It's not showing right now, but it should have like a counting that is still running. Once you show up the number, it indicates that is done. I had already installed it, so I get this, but most likely in your environment is not installed yet, so you will get a series of messages that is all done and then you have installed it. Then we are going to call the libraries that we are going to use in this notebook. And if you haven't installed it, this is going to give you an error because we are calling this specific library, which is the CF array. Okay. Similar to the previous notebooks, we are going to log into Air Data Search. Using this. And now we are going to start exploring the PACE surface reflectance data. As any other NASA mission, there are different data products available for the mission. So first, we are going to explore the collections, or just to see what is available related to surface reflectance. And we are going to run this. And we are going to use a keyword, in this case, PACE surface reflectance. And this is going to pull collections within the PACE OCI instrument that has surface reflectance. And there are about nine different collections. You can explore those different collections, and the structure is going to be a little bit fuzzy, but you can organize that in a better way with this code. And this is just to have an idea of the different data products that are available for PACE OCI related to surface reflectance. As Eric mentioned before, we had the short name, the collection concept ID. I think it's the best practice to use the collection concept ID because this is the unique identifier for any collection. The data that we are going to work with is PACE OCI level 2 surface reflectance. You can see that there are other level products like level 3, near real-time surface reflectance, and another over here, but this is the one that we are going to use. So this has the native resolution of 1.2 kilometer a meter, and is already atmospherically correct. Then we are going to search for an image similar to the concepts, that were explained before by Eric and Aya. So based on a time frame and on a location, I'm based in Huntsville, Alabama with Emil. So I put some coordinates that are around the state of Alabama here, and some recent dates in terms of time. And now I know that the short name for this specific data product is PACE OCI level 2 VSWIR EFL. So that's where we're going to enter here, indicate the version. And Eric and Masa can correct me, but if you use the unique, the collection concept ID, it is already the unique identifier. So maybe you can not worry about the version. Something also that I would like to mention here is that when you are accessing the data directly from the NASA DAACs or through Earth Data Search, you can access the latest version of the data. There are always updates that are being done to these datasets to improve its quality, and that's why we have different versions. And it's only through these repositories that you can access the latest information that is available for a specific data product. You can also filter by clouds. You can change this if you want to see all the images that are available that touch this location in this time frame. You can change this to 100. I'm sorry, but I'm going to leave it to 0 to 50%, and we are going to run this. So it indicates there are about 10 images that have these characteristics. If I change this, so this is going to pull all the images that are available that touch that location in that time frame, and you see that there are 27. I'm going to leave this to 50. So we can start exploring the data here. Everything was saved on a list called results. So I'm going to access the first one. And because I'm logging in Air Data Search, I can actually, if I click here, I can download that product directly to my computer. But I'm not going to do it. Just want to show that. We can also explore the metadata. And this is a dictionary, but we will need to know what type of information, what are the keys for that dictionary to see how the metadata is stored. So you can run this and you can see that these are the keys. So if you want to explore the metadata, you can call for the key call method, which is the one available here, and have more information about the specific data set. And this is for one granule. You can also download the data. Here, let's access the first 5 granules in this original list, and we have about 10. And if you click on this, you can automatically download each of these granules. Okay, this is something similar to the EMIT notebook, where we are going to work kind of on the fly remotely with the data. We are not downloading the image. To make the notebook faster, Eric has included this code that makes everything run smoothly. Even though we have so many participants, it still may take some time. But this saves the data into memory in this environment. And these images are not as large as the EMIT images, but it's not the best recommendation. But for this exercise, we are going to do it this way. So we're going to run this to connect to the remote file and read it into memory. These 2 cells are going to enable that. And that's going to make just this process a little bit smoother. Still running. And now we are going to open the data. Similar to me, this is also NetCDF, so it's in a hierarchical type of a structure. And right now we are just going to open the PACE data level 2 surface reflectance. So if you see it here, is in the data is organized in different groups, and we will need to restructure this in able to be able to read it better. But this gives us an information of how the data is structured and the different groups. We have a group, for example, here that is called sensor band parameters, that it has the coordinates, the wavelengths as a coordinate, and it has these different data variables. And you can explore here. Something critical here is the geophysical data, which is a different group. And this has the data variables that we care about. The rows represent surface reflectance, and the level 2 flags are the quality information banks for these specific data sets. But you see, it's a different group, has these dimensions. This is SWOT data, something to be aware of, because it does have a geolocation information, but it's in the SWOT format. So it's a little bit raw, and we will go through the process to grid it, so to be able to manage it better. But this is the structure of the level 2 data set. So right now, this is just opening the data set, exploring it, and see the different groups. And then, based on this information, we are going to structure in only one data set and call the groups that we care about that contain the information, the data, the geophysical data variables that we care about, and also assigns the latitude and longitude as the coordinates for the data set. So this is what this code is doing, is creating a data set that collects the groups that we care about with the data variables that we care about. So we are going to select the data of surface reflectance and quality information, the sensor band parameters that includes the wavelength, and the navigation data contains the longitude and latitude, and assign those as the coordinates. So now we create this new data set that has this structure, these dimensions. Is a three-dimensional array. And we have these coordinates, and we have the data variables here that we care about. This is what we have created reading the NetCDF in this way. So to explore just the wavelengths that we have available in the PACE OCI instrument, we can select the index of the wavelength 3D, which is here, and just see the bands that are available. So I think that this is referring to the center band, and based at the very beginning of my intervention today, remember that these are the very close to each other measurements that go from 340 to 895 consecutive measurements, and then we have multispectral measurements here from these other bands that are shortwave infrared. Okay, so now with this new structure, we can plot the data just as it is. But remember, this is SWOT format. So we can select the data variable that has the surface reflectance in the data set, and we are going to select a band. We are going to select the A60 in this case, which is the near-infrared one, and we are just going to plot it here. And I want to thank both DAACs, the OB.DAAC. We are repurposing code that has been created by the ocean biology that hosts the PACE data, and also code from the NASA LWIR in this Jupyter notebook. So here we can see just the image, and in the SWOT format, we can plot it because we have longitude and latitude information for each of the observations, very precise measurements, but is not gridded or tiled yet. We can also explore, here we created a variable with this name that contains the surface reflectance at this spectral band. So you can explore the structure of that particular X-array over here. And next we are going to apply the cloud mask. So we saw that in addition to the surface reflectance, there is another data variable that is contained in this dataset that we are dealing with, which is called L2_flags, and that has the quality information. So let's see what we have here. We can see the different flag masks and what is the meaning for each of them. You can see that there is a mask for land, clouds, and others. And in the ATVD, you can find more information for each of these flags. What we are going to do is apply that quality information to each of the observations, so then we can mask all the clouds and select everything that is only land. So we're going to remove water because the land mask is only going to pick up the pixels that have land, and we are going to remove the clouds and ice using these flags. And then we apply that mask to our data set, and we are going to give it a different name. And what we are going to obtain is a layer that only have land pixels, free of clouds and or ice. But given the location that we have and the time frame, I don't think that we'll have ice, but that's different. And then we can plot this, the masked data set. Remember, this is still in SWOT format, so it's not gridded. To manipulate the data, as we are used to with any geospatial data set, we will need to reproject this information to transform it from SWOT format to a gridded format. And we are going to use a simple method here, but there are other steps that you can follow. You can use CDAS, and there are also specific Jupyter notebooks that PACE has available as part of the PACE tutorials that you can follow to reproject these data sets. This is going to reproject the data based on the lat long. Is going to use WGS 84 as the datum, and it's still geographic. It's going to work for this image, but if you want to do some time series analysis you may need to do this more carefully. By the way, you saw in the EMIT tutorial that they are using a lookup table. We don't have the lookup table to have that reprojection here. So just be aware. The first step would be to put the band information before. If you saw on the data structure above, the band information was at the end over here. So we are going to put it at the very beginning. And that's what we are going to do in the cell. And then we are going to reproject. All of these steps are the main purpose is to reproject this data in a gridded format, so we can manipulate it better. If you see, what we are seeing is lines, number of lines and pixels per line. So it's not that intuitive if we want to do some normal geospatial analysis. And now, did I run this? Yeah. I think I had already run it on just. Yeah. We can see the new structure. So now we do have the band information in the front, but we also have assigned latitude and longitude. If you see the data structure here below, is our lat and long are no longer in two-dimensional arrays. This is a gridded data set now as compared to SWOT data. So now that we have the data in a gridded format, it will be easier to manipulate and do additional processing. So we can create an RGB image, selecting some bands that represent red, green, and blue, and that's what we're going to do here. And this function is going to help us to adjust the brightness of this RGB. We are going to apply it to the selected bands and then plot it with HBplot. That is going to give us this dynamic plot, which is pretty neat. So now you can see here, you can click here and zoom in and zoom out the location. This is an true color from PACE, and you can navigate through the image. Okay, now we can also plot the spectra, similar to what we did in the EMIT notebook. Remember that these are about 1.2 kilometer pixels. So as compared to the 60 meter from EMIT. So after you run this, maybe it takes a little bit longer on your end. I got greedy. I use a big computer here so we can go fast. But over here you can dynamically hover over the map, and you can zoom in and collect this spectra. And this is very nice that we can do this. For example, if you want to use hyperspectral data for your own analysis, you want to map a specific pigment, you want to identify even for land cover, wherever you need to do, you know that we always need to collect the reflectance for known locations where we know the existence or absence of specific variable that we are mapping. So you can collect those over here and then export this spectra. So please note that here I am only plotting from the 340 to 9 to 895 wetlands. We know that we have more bands, so you can comment this, but these are the continuous measurements, right? And once we expand this to This 25. You can see the bands here. You can change that limit here. Just remember that those other measurements over here in the longer part of the spectrum are multispectral. There are not there are specific bands. They are not like these. They are consecutive. So when we are looking at the profile of the surface reflectance, it's better to have it in the consecutive measurements here of the spectrometer. Just FYI. But once you have collected some relevance spectra, you can save that. And all of this is saved in the points stream variable, and you can save it as a CSV file and use it to train a machine learning model or for any further step. So that's and this is very neat, and I want to thank Eric and Masa for getting this to work with the PACE data. So now we can calculate unique indices that are enabled by this hyperspectral data. This is also some higher level products, by the way, that PACE is providing as level 3, but is at a coarser spatial resolution. Here we are creating them with the native 1.2 kilometer spatial resolution of the data, the level 2 one. Now that we know we have our data in a easy format to deal with, we can calculate some indices, like similar to the indices that we use with multispectral data. There are some unique ones that are enabled by hyperspectral data. The mission is providing a number of those hyperspectral enabled vegetation indices. I'm only going to work with 2, but now that you have access to this, you can calculate your own. You can check the ATVD and the different vegetation indices that they are proposing or they are using here. So the first one is the chlorophyll index red H. This is similar, but not exactly like NDVI. It has more sensitivity to chlorophyll content. So you're going to see that the range is higher. So NDVI saturates because it's just the red and near-infrared band, but this is just in a near-infrared bands. We know that plants reflect a lot in the near-infrared part of the electromagnetic spectrum, and by using these very narrow bands in the near-infrared, we have more sensitivity to chlorophyll content in a more quantitative way. So think of this useful for agriculture applications, or for forestry applications, to evaluate the health of your plant, and is not saturating as NDVI does. And the other index that they propose is the carotenoid content index. Carotenoids is another pigment present in plants, and we can use this equation, and I'm taking this directly from the ATVDs that PACE proposes. And this is very easy. We just select the bands and then apply the equation and then give it a name, and we have our index. So I'm going to go through this fast, and then we plot the data. And these are indices that you cannot create with multispectral data from Landsat or from MODIS, for example. And you can explore here. You see the scale is different of what you will expect with NDVI. And you can zoom in and zoom out here and see the specific values for the pixels that you are evaluating. So this is very, very nice. Then we do the same for the carotenoid content index, vegetation index, because it uses 2 other wetlands that we have already used in the SIRE, in the chlorophyll index red H. We only need to select the other band that is not used in the previous one, and then we calculate it, and then we map it, we plot it. once our data is created, it's way easier to deal with. And depends of the type of vegetation that you're looking at, the season, these values are going to vary. So this is unique information that you can use that you didn't have access before. So this is very, very, very neat. And this may be a simplified way to use hyperspectral data because you can use the whole spectra, but there are unique indices that give you information for things that you care about, such as this, that we can create that otherwise we couldn't. Okay, so and then you can, to have something more dynamic, you can also compare both and explore the values of both type of pigments at the same time. So if you click here, you can zoom in, zoom out, the same location. And with this information, you can calculate your own index and plot it right here. So thank you so much. I don't know how we are on time, but
Hey, Africa, there is one question. Can we use other hyperspectral data to calculate these indices?
yes, yeah. We see that for the bands that we are using here, those are also available with the EMIT data, so you can calculate these indices with the EMIT data too. And we are going to do it in GEE, in our GEE tutorial.
A follow-up question is, do you have any list of formulas to calculate more such bioindices?
Yeah, I would recommend to visit the ATVD from the PACE surface reflectance. Well, there is, all the ATVDs are there online, and they have a list of indices that they recommend for hyperspectral. But in addition, I think this is domain specific. I know for aquatic applications, I work with water quality. And one big issue that we have is how to distinguish algal blooms that are toxic from those that are not toxic. So there are specific pigment in some of the algae, such as phycocyanin type of content that may indicate if there is a toxic algae or not, and that has a unique spectral signature that has some unique absorption bands and reflectance bands, and then some indices are used on those points where we expect to reflect more and where we expect to absorb more. So I think that it will depend on your application. There will be a plethora of unique indices that you can use for your application. But for this one, there are some general vegetation indices that are recommended and that are already created at Quartzer spatial resolution from the PACE mission. And you can check, this may not be the specific one for the vegetation indices, but I'm going to put it in the chat. But you can find everything there in this site. Go to other activities.
Thank you, Africa. There's another question actually that was posted in the chat just a couple of minutes ago. And the question is, sorry if this is a redundant question, but just to confirm, are all of the packages suitable for use in our local Python environments?
And maybe Eric or Masa would like to respond that.
Yes. The answer is yes. And there's an environment.yaml file that you can use in the repository. And also on the webbook, there, and under the setup instructions on the left side, there's a local Python environment setup, and that's got instructions that you can use to set up this stuff so it'll work locally. And I just pasted that link. Oh, somebody else beat me to it. Anyway, just pasted that link in the chat for everybody.
Great. There are additional questions?
I see one that is not responded. It's how to use the aerosol feature of PACE.
Aerosol, I don't know, but we can ask.
Yes, I did just put a link in the chat to the dataset landing page for PACE data. And if the participant goes to that link, you'll see that there is an aerosol properties link where you can learn more about those products. So hopefully that helps a little bit, but certainly we can follow up with Morgane with some additional details as well.
All right. So, because we also have some tutorials in GE, and I think that's the next step. Just let me do a quick recap because we are about to change cloud environments. So, and we are good on time now. We are right on time. So this is.
Can we also have everybody shut down once they're done with the Jupyter Hub?
Yeah, let me do that then. Yeah, let's see here. So, Eric, this is how I do it. Step is, but you want also to completely.
Share to your screen, Africa.
Oh, sorry. I just stopped running the notebook. And now because it is already stopped. It's not there, but then you can shut down here.
Yeah, you can close those kernels, but if you also go to File and
okay, yeah.
oh, you're on the OpenScapes one. You're not on the workshop.
Yeah.
Okay, but everybody else can stop it. I see. Okay.
Yeah, that's why it's running fast. But, there. Okay, so that's how you can stop your server. And now I'm going to transition to just a quick remarks about transitioning cloud environments. So what we have done so far has been based on NASA Air Data Search. And here we are accessing the data directly from NASA repositories. So we know the formats, all the documentation that is out there is referring to these specific datasets. We know the science. We heard the presentations yesterday, for example, for David and for Glenn regarding to EMIT and ECOSTRESS, respectively. But we have similar information for all the other datasets that are available through NASA. And we know of the issues as well, and those are reported as we are made aware. Then all NASA-produced data is there. Eric mentioned the CMR catalog that enables all of this. As I mentioned, every time there are new versions of these data sets as things are improved or the quality of the data is improved, and the latest version of the different data products are available in these repositories. As you saw with the exercises that we went through, we need to be aware of the data formats that we are dealing with. And different data products may have different data formats. We may be dealing with SWOT data, with gridded data, with tile data, but all that documentation is there. But we need to take that into account when we are accessing and processing the data. And as it was mentioned previously, all NASA data is being moved to the cloud. So that means that setting up in your own cloud environment, you can access all the NASA data sets. That's what we have done so far through these Jupyter notebooks. Now we are going to transition to Google Earth Engine. And this is commercial, like AWS is also commercial. But it contains data from multiple data sources, not only NASA. In addition, it doesn't have all NASA data sets. Yesterday, there were a lot of questions about is ECOSTRESS data there, is space data there, is EMIT data there. Well, for example, for the 3 data sets that we are exploring today, what Google Earth Engine has ingested officially is the EMIT data. We are going to be working with PACE data, but thanks to Emil, because he has uploaded already some PACE images into Google Earth Engine. And you can do that yourself as well with other datasets that may not be available there. But this is just a reminder that not all NASA datasets are available in GEE. Then this is the point that the data needs to be ingested. Sometimes they do it, some like of the official collections that are already there. And if there is not, you can do it yourself as well. What is very neat for GEE is that allows a seamless integration of multiple data sources. And for all of us that have been dealing with GEE for some time, it's relatively very easy. You don't have to be thinking about projections and resolutions or other things of different data sets. You can bring all together as long as it's in the Google Earth Engine platform. But the way to do that is that Google Earth Engine uses a sophisticated pool-based system and internal image pyramid structure. So they are ingesting the data in their native projection, and then they create this image pyramid structure that are like on the fly, enabling the data to be seen on the same platform. Once you do a process, it does a smart reprojection of the data. So because when you do geospatial analysis, you have to have everything on the same projection. But this is not reprojecting everything to make it visible in the same grid, to say it in a way. You are just seeing it thanks to this image pyramid structure that is available like at different scales depending upon of the zoom that you have. That is like a mirror. I don't want to say magic, but it's that this is the way that they have enabled this. And once you actually do an analysis, it's going to reproject the different data sources, so you can do that analysis, but you don't have to think about it. You just run the thing without thinking what is going on in the background. So that's what we call the output-driven projection. That is this pool system that is enabling this reprojection just when it's necessary, just when it's doing a processing, and you actually don't have to think about it. You just run your stuff. So in my personal experience, GE has been great. It's excellent for prototyping and testing new methodologies, particularly those that require multiple sensor data. And if you are doing a one-time analysis, this may be very, very useful and powerful. If you are testing new methodologies, extremely useful and powerful. But for operational purposes, large-scale purposes, when you have your pipeline, your workflow, and you know, okay, this is what I need to do to the data, and it gives me the product that I need, but you need to do that at large scale and on the routine basis every week, every day. There may be some, it may be too costly if you do it in GE. You may need to explore other solutions, such as those in other platforms, because it's easier and less costly if you run this analysis in the cloud once you are closer to the data. And that's why for operational purposes, many times it's more cost effective to run your pipelines when you are pinning the data in AWS, because closer to the bucket where the NASA data is. That's what we have experienced on the ground. So as Emil mentioned, we are not favoring one cloud provider over another, but we just want to present the realities of what we have experienced. GE is super powerful, but if all of this has a cost associated, we are in a training, so we can use the non-commercial license. But once you have your operational purposes, you may need to pay. Most likely you will need to pay because it's a commercial provider and you are using cloud resources. And because of the structure of it, these processes may be more computational intensive than if you do it yourself over here. Or obviously on the other cloud component, you will need more code. You will need to be aware of everything, but you have more control over the process as well. We just want to make that clarification, and then I pass it to Emil to work on GE. Thank you.
So I don't know if this is possible, but we did have and maybe other participants feel the same way, had requested if we could take like a 1 to 2 minute break before we start the next section. I don't know if we can manage that or not. I defer to you.
Yeah, I think that makes sense. Yeah. They have been
okay. I think that could be good. Then people can, stand up for a minute and stretch or what have you. Thanks so much, everybody. And then we'll regroup in like a minute or two.
Or maybe even like in 5 minutes, if people want it. I'm ready to start whenever, but I think I can also compress my material to catch us up.
Sure, that sounds good. Is that okay with you, Africa?
That sounds good. Yeah.
Okay, so we'll regroup at 3:45.
Hi, everybody, again. I guess since we said 45 after the hour or 15 minutes to the next hour, I guess I'm ready to start. And again, I'll try to compress a little bit to make up for time. So I hope everybody is doing well. I know for some people who might be on the other side of the world, this might be a little bit late. As Jennifer indicated, the nice thing is that all of this will be recorded. So for those who might have had to drop off early, you'll still be able to see this afterwards. So I hope everybody can hear me, and I think everybody can see my screen. I guess the first thing I was going to just quickly kind of back up and mention, I know that earlier, and thank you for the thumbs up. Earlier, there were questions about the different steps, etc. So again, the vitals page that Eric and Masa had put together, there'll be links to the resources there. However, I just also wanted to mention that a number of these things I've loaded as GitHub repositories, which I think some people had already found their way to. And so for those who might have missed it or wanted to go back over it, just to say that the presentation I gave, the overview of Earth Engine yesterday, and the one that I repeated today with the process for registering Google Cloud projects for Earth Engine, that's there. And then just in case you're wondering or need that link, my GitHub is BZGeo. There's a repositories link there, and there's a number of things there, including this PACE toolkit that I'll be showing, although in Earth Engine, and then some helper things that go along with that. But just to say, feel free to have a look over there. And again, just because of the mode this is in, I can't see the chat. But Africa, Eric, Masa, Jennifer, others, please feel free to step in and let me know. And I can see that Masa just reshared the link to the vitals page where the different links are. Just backing up just a little bit and trying to complement the excellent presentations that were given by Eric and Masa and Aya and Africa. And then also going back to yesterday, Morgane presenting about the PACE work. I think that some people are familiar with NASA's Worldview, as it's called, worldview.earthdata.nasa.gov. By default, when you log into into Worldview, you're going to see MODIS imagery. However, there is an add layers option, and you can add PACE reflectance data as well as chlorophyll data from PACE. And for instance, if I zoom to if I zoom to yesterday, the 21st, for whatever reason, I'm seeing it looks like the Chlorophyll data hasn't fully been ingested yet, but we can see the imagery captured yesterday. It looks like there might be issues for the day before. But if we look at the data from Saturday, the 19th of July, we can see both the reflectance imagery as well as the chlorophyll. And at least for myself, as mentioned before, I'm a PACE early adopter. One of the ways that I've always found to be able to find really neat samples for PACE imagery is just going to Worldview and, looking at a specific date, or just using this bar to scroll through and find when there might be imagery. And I know yesterday in the chat, it looks like there was a colleague from Kenya asking about how to find, decent imagery from PACE over Kenya. And so what I did yesterday is I also just opened up Worldview, zoomed in, and looked around. Again, this just being a browser, also as Morgan said, that will just allow you to kind of see what is out there. However, just again noting that a lot of the people who are on this webinar, you are interested in, seeing what data is out there, and that's something we're going to look at in just a little bit with Google Earth Engine. So I'll close that off. The other thing I wanted to mention really quickly, and it does tie back into, what I'll be showing with Earth Engine, is as Africa just recently mentioned in her last bit, she talked about the OB.DAAC. I'm sorry. Also, I believe Eric talked about this as one of the different NASA distributed active archive centers. And in case you have the time to kind of look at that link, it's oceandata.sci.gsfc.nasa.gov, and specifically /L3/. It takes you to something called the level 3 and level 4 browser. And when you open this, by default, it's not showing PACE data. However, if you change to provisional, you will be able to see PACE imagery, and the imagery that, specifically that we've been looking at. There's surface reflectance data. So it, let's see, it's for some reason still showing me chlorophyll data. Okay, now the surface reflectance has come up, and we can see that, the imagery being, updated, etc. And just to mention quickly, and we're not really going to get into this, but using this level 3 and a level 4 browser, we can download data in NetCDF format from here. Realizing, of course, that many of the people around the world, you might not necessarily, want to use NetCDF data in your desktop GIS systems. However, in addition to that, just to quickly mention that, there's also the land vegetation index data. And we saw, what Africa showed with some of the different indices that she was able to generate. This is showing you NDVI data. However, the product that you're able to extract, for instance, just to show people, if I were to click that and click mapped and then click that download button, it gives me a list of basically all of the daily land vegetation index data starting from March of last year to the 20th, which was Sunday. But again, this data is in NetCDF format. And again, many people, particularly who are using GIS and doing remote sensing, NetCDF isn't the format that you prefer. However, just also going back to something that Africa was showing, where PACE data comes in multiple different formats. Out of the level 3 and level 4 browser, the highest spatial resolution data sets we're going to get are 2 kilometers, the standard, and then they only recently started producing this 2 kilometer data, I believe, back in May. You can also get data at 0.1 degrees, which is around 11 kilometers, also 4 kilometer data. I'm just going to close that off, but as to say, here's where we were starting to get data, or when we got the data for what we're calling the PACE OCI Toolkit, which I'll be walking you through in just a few minutes. Again, there's a good GitHub page for this as well. And as Africa was pointing out, where Google Earth Engine is this, computing platform that also provides you access to other types of data. Earth Engine also has archived Hyperion data, which covers data from 2001 to 2017, EMIT data, And the big difference between PACE and EMIT and Hyperion is that essentially the people who are running those missions need to essentially turn on and activate the sensors to capture new data. In the case of Hyperion, it's no longer functioning, but EMIT, my understanding is that's how it works. Somebody has to say, okay, we're going to capture some EMIT data. It's not that it's always capturing it. And so yesterday in the chat, when I said I considered EMIT and ECOSTRESS an on-demand sensor, that's what I meant by that, is that they're not always capturing data compared to, say, PACE or Landsat, MODIS, VSWIRs, which are always imaging the Earth. And then the only other thing, I guess, well, before we start to look into the toolkit, I'd also mention is as part of the toolkit, just to explain to you the kind of the workflow that we've taken and how we've been doing this. On this side at Marshall and at UAH, we've been grabbing PACE OCI data specifically from the OB.DAAC, well, OB.DAAC in some cases, LP.DAAC in other cases, surface reflectance data, vegetation index data, downloading that in that CDF format, using either CDAS, which is a NASA software built on another software called SNAP, which is from ESA, or SNAP itself, to export that data in GeoTIFF format, and then uploading that data in GeoTIFF format into GEE, doing a few processes like rescaling the data or compositing it, etc., generating image collections, also internally, like looking at the data to make sure it's good, making those data sets public, and then pushing it out as part of this toolkit, as you'll see in just a moment. And I guess just previous to jumping into Earth Engine, and I promise we'll get into Earth Engine in just a wee bit, also in terms of the other GitHub repositories that I have under my account, something that Africa specifically had been asking about as we were discussing this event was kind of, well, how did you take the data using SNAP or using CDAS and convert that over? And so one of the things that I've posted there in GitHub is how to use SNAP or CDAS to process that data, actually more specifically CDAS, with the idea being that a number of you out there, might be just, desktop GIS users. You want to have that data on your desktop. How do you walk through that? So there's a whole kind of walkthrough there. There are, slides that you can check out, etc. And yeah, this is just showing what the slides are and me, kind of showing the whole setup using the LP.DAAC, for instance, to grab the surface reflectance data, etc. Not going to get into all of that. I'm going to close that off in the interest of time. And then there's another, I also have an R script for automated conversion of the land vegetation index data, spitting those out into GeoTIFF formats instead of using SNAP or CDAS. Close that off. Just before I jump into the Earth Engine stuff, just a few other things to mention. As Morgane mentioned, again, I see, okay, thank you, Eric, for the clarification of that. And I'm not going to take like the full time allotted, and maybe Eric and Masa can go into the details of, I guess, what constitutes on demand, et cetera, et cetera. But I think the bigger idea is simply that PACE is always grabbing imagery all the time. And so you're guaranteed to get imagery on a certain interval, which is roughly daily, versus EMIT, which is not getting you imagery on an interval like some of the other ones. As Morgane pointed out yesterday, they've started up different communities of practice for different uses of PACE data. One of them is called the Plug, or the PACE Land Data User Group. Plug has already had 2 virtual meetings so far, one in April, one in July. I also got to present the work of the toolkit there. You can go to the PACE page and find out more information on that. But more so than that, if you're really interested in you continuing to use PACE land data, I would encourage you to sign up to the different PACE communities of practice. There's a community of practice link on the PACE page where you can sign up to continue getting emails about that. I know that Morgane mentioned that yesterday as well. And then just, I promise you I'll jump to the Earth Engine stuff. One other thing to mention is, in addition to this webinar that we're doing, we also have another specific walkthrough of the PACE data in GEE 2 weeks from tomorrow on the 6th of August in conjunction with AmeriGeo Week 2025 as a pre-event. And in case you're wondering where you can find the registration link, et cetera, the PACE Toolkit GitHub page, you can just scroll down and there's a link to the registration there. That's where you can find that. I will close that off. And then before I jump into the Earth Engine stuff, I promise, in just a moment, one thing that I wanted to mention, I'll show this in just a second. The toolkit that we're going to be looking at has 3 dependency packages, and I'll walk through those in just a wee bit. One is different types of functions, including the indices, kind of like the equations for the indices that Africa started talking about. She showed you the chlorophyll index red edge, for instance, or SIRE. That's one of the indices that's there in that package. There's also a data loader package where essentially I manually am uploading or updating it with new data that's loaded. I should also mention that there's a lot of PACE data simply because that data is updated on a daily basis. The data that we are loading, however, into Earth Engine is not daily. So some of the data, the surface reflectance data sets, we're only putting monthly data and globally, as well as for the continental US and Mesoamerica. And if you ask why we're only doing it monthly, the data are really, really heavy. However, the vegetation indices, we are loading not only the monthly data globally, but also the 8-day data. And in that case, we're only loading the full kilometer data because the 2-kilometer data is not available for the full time series. And that other slide says the same thing. If you're wondering where you can find this slide, again, the Toolkit GitHub page, there's a documentation folder where I have 2 PDFs you can check out. And I also noticed a few people already checked out the page and gave it stars. You folks are awesome. Alrighty, that said, if everybody had clicked that link that was shared before, and unfortunately, it's hard for me to, again, get to the chat. There was a bit.ly link that was shared before. That bit.ly link should have taken you to something that shows code.earthengine or google.com/accept repo equals user severe bz pace _OCI. A few people had in the Q&A indicated that we're getting errors, and then some other smart people in the Q&A had figured out that all you had needed to do to remove the error was to refresh your page. So that said, I hope that everybody is able to see that. I just wanted to maybe quickly, before we start clicking around and using these, and I know that Africa also has a really cool example, some examples coming up that combine PACE and EMIT. Before that, I just wanted to again show those helper functions. And so I have another repo called the Hyperspectral Data Toolkit. And then just to quickly show, contains information like the wavelengths for PACE, wavelengths for MODIS, wavelengths for EMIT, wavelengths for Hyperion, some other things that kind of allow us to filter through some of these data sets. Band combinations for quick viewing of data. So one of the things with Earth Engine, when we load the data, we will have to specify how we want to view it. And then the calculations for the different indices, most of which are the standard PACE ones, but also a few other ones. Also for rescaling data sets. And let's see, doing some other things like principal component analysis, etc., etc. With that, I can close that off. And before we start getting our hands on the data, lastly, again, just to say there's another helper script there that loads the different data sets there, whether it be for, specific scenes for parts of the continental US, all of the continental US, Mesoamerica, global data sets that are updated to June, the vegetation index data, which are updated to pretty much the last dates which are there for that data. So it's 8-day data that was last updated on the 19th of July, which was on Saturday. And then other, just things for putting those things together as image collections. And then another script where I've loaded some sample locations. And again, apologies if I'm going a little quickly through all of this. I'll close that off. I will also close off the link to the GitHub repo. And again, I hope everybody is able to, again, see this repository. And I guess the first thing I wanted to do was kind of walk you through some of these things. And again, Africa has also some cool tutorial stuff to show us in about 20 something minutes. Yeah. So one of the first, so similar to, and I guess one thing to mention is that we imagined this set of exercises, the ones that I'm going to show you and what Africa will show you really shortly, is for this to be complementary to what we saw with Eric and Aya and Masa, with the other notebooks. For instance, if you were to, and again, you're all in there, you see the different scripts. I would encourage you to maybe let's click on the second script that says count images all NASA Hyper USAL HSV. And in case you were wondering, just saying, all NASA hyperspectral assets that are in Earth Engine for the US, state of Alabama. HSV is short for Huntsville. I have loaded the coordinates for Huntsville, Alabama. And as something I just mentioned before, yesterday, is one of the neat things about Earth Engine is there's a little inspector button there. If, for instance, somebody like Diego from the Universidad del Valle is calling in, Diego is, I believe, logging into us from Guatemala City. If he wanted to, he could click that inspector button, or of course you can select any place you want. You click that inspector button. It will give you some coordinates. You can copy those, Control C, and paste them in, and it will, when we hit run, it will show us what data are available for that area. I undid the change that I did just now, but all I'm going to do is hit that run button. And just following on to what Africa said, one of the interesting things about Earth Engine is, for the most part, you don't have to worry about libraries and functions, etc., being loaded. Although in this case, I've specified a package. I only have a model on. Okay, I see Clay's comment that you can only see. All right. As mentioned before, for those who might not be able to see. Okay. And the other thing as well, for people who are logged on online, you will likely see this repository that says PACE OCI under Reader. The reason why I'm seeing it under Owner is because I own because it's my repository and other people are reading this. And so for everybody else, you should see, if you would, successfully loaded, it should be under your Reader list. You'll see I have a huge set of repositories, including from Africa, et cetera, et cetera. And so I hope, Clay, that if you click under Reader, that you see one called User Server BZ PACE OCI. Okay, I see a thumbs up. Thank you so much. You see I had hit that run button, and Clay, I believe, is in the building as well here. So what NASA hyperspectral data are there for Huntsville, Alabama? In this case, I should also just mention quickly, I've specified based on this package that I've put together, I want to know what archived Hyperion data are there, also what data from EMIT are there, but also not just the surface reflectance data from PACE, but also vegetation index, in this case, EVI, or the Enhanced Vegetation Index. Again, hopefully I'm not going too fast. In this case, these results will print in your console. Yes, Jennifer, we can pause for a question.
Okay, so there are several users who are not seeing any of these repositories at all. Okay. So I don't know if you could backtrack just for a minute. I did place the bit.ly link in the chat a couple of times, and also
sure.
If you could maybe provide just a quick recap, that would be great. Some participants do think the speed is a little bit too quick.
Okay, thank you. And I'm finding the chat. So I have just posted again the bit.ly link in the chat. And when I'm going to pull up, I will open up Earth Engine with a different account. So if everybody can give me.
Thanks so much for doing this, Emil.
No, thank you for pausing me. I do listen to my podcast at extra high speed, and I also talk it at high speed. So sorry about that. Okay, let me share my screen again. All right. So hopefully, I think most people, you should have a window when you open code.earthengine.google.com. And if you're not there, maybe I can, again, I think the only way for me to see the chat is for me to stop this and pull up the chat. So let me just post that link there, and then I will show my screen again. And so if you're there at code.earthengine.google.com, if you had earlier used the bit.ly link and you had refreshed your repo, again, you might have to do this. It was a colleague of ours, Diego Insa, who's joining us virtually from Guatemala. He was the one in a workshop a few years ago who had, it's like, have you tried clicking that refresh button? And usually the refresh button, it will refresh your list of repositories. And earlier I know that other people, when they had tried adding the repo, got an error. If that is so, just go up to your code.earthengine.google.com and click enter again, and hopefully everything gets resolved. And if people are able to see the PACE OCI repo and wouldn't mind giving a thumbs up, are people able to see it? I see somebody has a hand raised. Should we ask the person with the hand raised should we get them to unmute or post the question in the chat?
Yeah, if you have any questions, please enter those into either the Q&A panel or the chat. That would be wonderful. Thank you.
Okay. And so then, again, just going back, you will notice when you log in. So if everybody hopefully has been able to see this, and again, I know Africa is going to take some of this and take us into something more specific. My overall idea, again, given the limited time that we have with you, is just to kind of show you these different functions that are here and say, this is a resource that you can continue using afterwards in your, in your work or at home, etc. You will notice that there are these little arrows, as it were. With the different arrows, you can click those, and then you will see those will expand and show us the different scripts that are there. The first script that I had tried was one that had a location for Huntsville, Alabama. Okay. Let's see, Digna. All righty. SDG AOI Globe is not loaded. Give me 1 second. Thank you for that one. How did I not figure out? Okay. Done. All right. Person who just posted that, if you would not mind refreshing, hopefully that took care of that. So this example is just, again, the one that shows us what data are there. The idea being just the same way how you might, you could use different types of tools to see what are there. You could use Worldview. You could use the awesome things that like that worked. This will just show you what types of images are there and the way how this script works. All right. And thank you, Diego. And of course, this is recorded and we'll be able to come back to it afterwards. It'll just give you a list of the dates of the different images that you want that you can then hopefully use in some of the other ones to then visualize the data, etc. And so, for instance, again, we're seeing the EMIT data. We see that they're, captured at different intervals over Huntsville, Alabama. We're looking at the monthly OCI surface reflectance data. We can see, and by the way how we list them is we list the last day of the month for those. And so we see that there's data from March of 2024 going all the way to the end of June. We're still in July, so that data is not out there. And then for the 8-day vegetation index data, we see the different end dates for those 8-day periods. Again, hopefully everybody's able to see those. And just to quickly say, there are other examples of, these date queries for French Guyana, an area in California called Paints Creek, where a fire occurred and where I believe Africa will be showing us her exercise, San Juan, Puerto Rico. And there's another script just for looking at PACE data over the US. Another one for looking at the footprints of EMIT data. Let me just see in interest of time. Apologies that I talk kind of fast. So similar to what Dana from JPL showed yesterday. Hopefully this one was a little quickly. This one is just showing you, how really hats off to the colleagues from JPL who are involved with the EMIT mission, and hopefully this will cooperate. There's just a lot of data for EMIT has been collected for different parts of the world. For instance, if any of you calling in are from Central America, you will see that practically all of Central America and maybe little slivers of Guatemala or slivers of Honduras, Costa Rica haven't been, but for the most part captured, compared to, if I can quickly go through this one, similar type of script, but now showing you the Hyperion data that had been captured between 2001 and 2017. We see that Hyperion didn't quite capture as much of different parts of the world as EMIT did. The other thing I wanted to show you to kind of prep us for the cool things we're going to see with Africa is just examples of visualizing EMIT data. So again, I know that Diego indicated that he had to leave. Have a script here that visualizes, that takes some of those same dates that we're able to consult from that other script. And then this one is just, now it's, takes the dates here and essentially shows us all of that. However, what we're seeing here is essentially just a mosaic of all of the dates. And again, apologies, and you could probably check it out in the recording. If I remove where I've commented out in lines 51 and 83, and I hit run again, I can now see the individual SWATs of data, and it's throwing errors for some of the dates that I have specified, which might be a reason why sometimes it's not good to do things like. Anyhow, that's one example. However, I think this one here, I'll abandon the changes. Another visualization example, there's an area close to where Africa I and other colleagues are located in Huntsville, an area called Paint Rock. And this one just shows you the different EMIT data sets, again, using the different dates that have been queried using other scripts, and also shows some spectral signatures. That all said, though, let me go back to, I think since we have quite an international audience here, let me click on, so again, let me just change my screen just a little bit. Under data viz, and if you can't see that, just click that little arrow looking thing. Viz PACE OCI 10 kilometer monthly globe. If we hit that run button, it will now zoom out to the entire world. And in just a little bit, will show us the PACE data that's there. If you do zoom to different also something that you might be able to see, it's looking a little pixelated in some areas, and that's because even though PACE captures data roughly daily, and these monthly mosaics are generated from the inputs are the daily data, they're not capturing everything. So there are data gaps rather because of cloud. However, the neat thing is you can again see, you can see the mosaics that are going all the way back to March of last year. And if you were so interested, you could click every single mosaic and check those out. The one thing I will mention though is, again, for issues of space and processing, in this toolkit, we've loaded the global data at 0.1 degree resolution, something around 10, 11 kilometers. And if you want the full kilometer data that you can grab from the OB.DAAC, which is higher spatial resolution, we've only unfortunately done that for Mesoamerica and the continental US. However, we do have some neat 1 kilometer examples for continental US. And just to kind of preview something that I believe we're going to see with Africa in just a little bit, just to show you some of that 1 kilometer data. And of course, Africa will take us through a comparison of what this data looks like in comparison to EMIT. And so, well, in this case, this script, we've only loaded 2 examples. For Mesoamerica, we have loaded some other, we've loaded images from other dates. We've also loaded some other data sets looking at ecosystem cover, etc. But it's just one of the neat things about this data is just it's based on what Africa had said, building off of that. The swaths for that data, for the PACE data, are wide, and so we can get large extents compared to the small swaths for other data sets. And again, here actually now it's we're comparing this original 1.2 kilometer data with an April mosaic, which if we were to zoom in, and again, I know that I'm not going to get to cover everything in the allotted time. Everybody now has access to this repository. Please, in your additional time, feel free to click around, and if you have any questions, do feel free to email me and some of the other trainers. And so, just a neat little example. If we look at this data, it does look pixelated, and that's at 1 kilometer. However, we look at the 4 kilometer data, it's of course even more pixelated because it's not as detailed as the 1 kilometer data. In addition to being able to, just view the different images that are there, again, we know that a lot of you want to analyze the data, and the colleague or the participant who found that one of the assets had not been shared had already, I believe, started looking at the gap filling or the time series scripts that are there. If we go now to spectral signatures, just, little interesting examples for you. Click again on another example from near the Huntsville area where a few of us are based. Again, all we have to do is select the script, click that run button. And in this case, okay. Actually looks like what I had clicked on was a comparison with MODIS. And so this stuff here, actually, we're not looking at PACE data whatsoever. We're just looking at MODIS data for June. You might not appreciate the stretch that I have on the imagery, which makes it look a little washed out. However, based on this pixel here, we are, and again, unfortunately, not going to get into the full details of that, but we can, program into the script a function for printing a chart. And for this area, which is, again, a state park called Montesano, which is to the east of Huntsville, we're able to see spectral signatures from this state park. Or what we're essentially seeing is how these spectral signatures change over time. And what we're looking at is, if I just go back here for a moment, we are taking, what are we looking at? We're essentially trying to match the period of the MODIS data that we're looking at with period of the PACE data. And we're looking at spectral signatures on a monthly time step. The first one here being March, April, May of 2024, going through to, I believe, June of 2025. And the big thing to note there is just we note that the shape or the form of the signatures changes over time. And maybe that's not the greatest example, but if I now click on the PACE OCI one, I think I can do a better job explaining this one. in terms of at least visualizing the spectral signatures. So let me pop that up. For those of you who might not be familiar with what the vegetation is like in the Huntsville or northern Alabama area, in certain months, say from October through March, the vegetation has lost its leaves. And so if I hover, by the way how these graphics work, and this is something that you can look at, if I hover over, we see that this month, the first month of data, which is March of 2024, it's this red line over here. Then April is over here. We see May over here at the very top. But basically, these months over here are months where there is little vegetation over Montesano State Park. And compared to the MODIS data that we were looking at before, the MODIS data noticed that the lines were pretty sharp, and that's because we aren't able to see the full spectra, or as full as you can see with PACE. And of course, the example that Africa will be showing us in just a few minutes, she's going to show how even more spectacular the spectra look using EMIT, which is hyperspectral also in the short wave infrared range. But the long and the short is from this, which are spectral signatures on a monthly basis, we can see that the month that has the brightest reflectance in this part of the spectrum, which corresponds to, this is the near infrared part of the spectrum. Over here, where we're having this highest reflectance, is in the May time frame, and this likely means to us that the leaves are brighter. The leaves, it's probably a denser concentration of leaves as well, and that's why it's showing us that in May things look brighter. And awesome, there have been questions in there, and thank you, Masa, for answering questions about downloading, whether it's CSV, we get the absolute data, or as graphics files, etc. I should start to wrap up just so I can pass off to Africa. But there are just different examples here, not just using PACE, as you saw, also using MODIS, using EMIT, an example here. And again, I'm not sure where all of the different participants are coming from, but if I hit, okay, looks like for this example, I did not have it zoomed to where we're looking at, but it's looking at changes in reflectance in mangroves over coastal Belize, and just kind of looking at how that signature has changed at different points in time. But again, apologies that we're not going to get into the full details of that. Africa does have some cool examples for us. Let's see. Again, going back to the example of Montesano State Park, a specific pixel over there that it's going to light up over here. Just a moment. One example that we're seeing here, and it's taking a little while to load. By the way, the 4-kilometer pixel that we're looking at over Montesano State Park corresponds to this area, which is rather huge and likely contains not just forest, but other things. But with the PACE data, if we're looking at that 8-day data, we can see the behavior of this vegetation index, the EVI, the enhanced vegetation index. You can see kind of where its peaks and throws are. You can see what that looks like in 8 days. We can see what that looks like monthly. We can see the, also the discrepancies between 8-day and monthly. And we can also actually look at all the different 10 different indices that the PACE team is putting out. EVI, SIRE, like we saw with Africa, as well as other ones. And there are descriptions provided for those. And lastly, in terms of example scripts, and again, encourage people to have a look around, test out the different scripts. If you have questions, let us know. Chrome didn't work.
Hi, Emil.
Yes.
Sorry, I misunderstood the question. So they are asking if they can download the map of the region of interest as a PNG, and they mean the actual map and not the spectral graph.
Well, I guess it depends on what you mean by map. So if they mean the actual spectral data, like the data from PACE or from EMIT, etc., that data, yes, can be easily extracted out of Earth Engine. If they're talking about, so like this imagery that we see here, as I had shown, actually, okay, it looks like I'd already closed that off. I had shown that there's a helper script, which is this one here that has like links to the images themselves. There's a simple function in Earth Engine to then take that data that's already loaded and export to drive or export to asset. So like, you can export to asset, basically loads it as a file in Earth Engine, but it could also be exported for, as a GeoTIFF for processing on the desktop. So yes, that is an option. And then, yeah, I hope that's useful. And then the last thing I was going to say, another example, or one of the different examples we have there, is for doing classification or testing classifications, kind of like Africa was saying, that the neat thing with Earth Engine is you can test different algorithms, etc. Looking at spectrally similar classes across these different data sets. That's an example that we have loaded there. I realize that I've probably gone a little fast, and there are probably a number of questions. In the interest of time, though, giving Africa time to hone in on her example, I guess I wanted to now pass the mic back. And yeah, and of course, if there are questions that people have in the chat, I'll also try to have a look at those. But thank you, everybody. I know it's been a bit to swallow, but yeah. Over to you, Africa.
Thank you so much, Emil. And maybe you can check in the Q&A panel for additional answers. So let me share my screen. So now that you have access to GEE, you can access the code Air Engine. You have access to this repository, which is Emil's repository. You may see it in the reader. I have it in the writer because he gave me access, so I can write and include some of my code there too. So what we are going to open is this EMIT PACE tutorial 01. Is in this folder called workshop _2025 07. You open this and you can see the EMIT PACE tutorial. You click on it and it's going to load the code. Let me open this. So we are going to explore some EMIT data. Emil has created very nice tools, and we are calling some of those libraries to visualize the information easily. I'm just going to walk you through the script. You can click here and it's going to run everything. So first, I'm calling some code from Emil. And we are going to explore an agricultural area where we have some data from PACE. And the data from PACE is as data that we are acquiring from the assets that Emil has uploaded. So you see in these three tabs here, here is where you store all of your scripts. On the scripts, docs provide information for the built-in functions that Google Earth Engine has, and assets work as your storage on the cloud. All this cloud asset and all the setting that you needed to do for a project is relatively new. For those of us that started using GEE some years ago, we just have the legacy assets, and now we have this new option, and you all have to have it. Well, so he has the data uploaded in his cloud assets, and we are accessing it. Just FYI for the PACE data. Because this has multiple data sets. For example, if you want to call, I'm pretty sure that many of you are very well acquainted with GEE. If you want to explore what is available for Landsat, you can write here and the different data collections pop up. But I want to just have an idea what is the land cover. So I I call for an NLCD, a land cover dataset that is actually created from USGS. And I'm just calling it as a variable. And then with this, I am mapping it, included in the map. Then I know that the location that I'm looking is going to be this one. You can change this, but for this exercise, I just want to walk you through how the EMIT data looks, how the PACE data looks, and what we can do with it. First of all is to just explore the EMIT data as GE reads it or sees it. So I give it a location that I explore. You can get very easily locations. You can click on any point on the map, and it gives you automatically a location, and you can include it in your script if you want to change. But let's not change right now. And this is pulling the point, centering the map over here, selecting a data range from January to May 2025. And now we are going to explore the EMIT data. So there are different image collections here. EMIT is available. If you write EMIT here, you are going to see the different collections that are available. We can close it. So we have the level 1 at sensor radiance and the level 2A estimated surface reflectance. And we are going to work with the level 2 surface reflectance. So what I'm doing in this code, I can actually do this. This is the name of the image collection. So on the ID, that's what we include here. We create a variable that calls for the whole image collection that includes everything, and we need to filter that for the location and the data range that we care about. So that's why we use these arguments, and then we can explore the EMIT data. So I printed this variable, and it's going to show here in the console, and we are going to see how many images are available. It's still reading it as an image collection, so it's a series of images. But in this case, it only found one image, which is this one, for that specific time frame and location. So we can see how GE looks at the data. So here in the properties is like the header of the information. Something that is different here is that you saw that when we access the data from Air Data Search, there was a cloud cover component at the image level. So this information, these properties, is applied at the image level. And we have the time, the system time start over here indicates when the data was acquired, is the timestamp for their data set. It's critical to maintain this because when we are filtering by date, we use this property. I don't see the cloud cover property at the image level here. Then let's check the bands, the spectral bands. So this contains all the spectral bands. If you see, it has 579 elements. And this is the name of the band that goes by index. So we can see that it has the reflectance from 0 to 284. And then it also has a reflectance uncertainty from 0 to 284. Correct. And in addition to that, the quality information that we saw in the EMIT data is also included as bands. And these are the names of the bands over here. So we saw with Eric earlier today, the cloud flag, the delayed cloud flag as well is over here. And also with David that explained that as a result to apply the atmospheric correction and the methodology, we get this quality band information. When it's here at the band level, it means that we can apply this information at the pixel level in how Google Earth Engine reads the data. So now we see the data structure, how it's reading all of our information. Because I only have one image in this image collection, but it's still considered an image collection because I give it this. I'm going to select only one image. I only have one, so I can select the first one is the only one. If you have more than one, you can transform this to a list and then select it by the index. And we are going to plot the data. By the way, in the properties, you can see this reflectance wavelengths property, and it contains the wavelength information that is associated to each of the bands. What we are going to do is going to use this information of this list. We are going to extract it as a list and then rename the bands appropriately, the ones that had the reflectance data, because it will be easier to manipulate the data that way. But in the meantime, let's say we have all those reflectance bands and it's reflectance. So we know that the values go from 0 to 1. I did my homework and I check, okay, what is a good RGB bands based on the index, but this is not intuitive. But here I am selecting some a band that represents the green and another that represents the blue, and I'm sorry, red, green, and blue over here, and then plot it. And we are going to get the EMIT true color one. So just to give you an idea, by the way, this is the location of my AG site. And if you activate the underlying land cover map, you can also see where we are looking over here. If you go here to the point, in the inspector is going to give you the value at that pixel level for all the layers that I am mapping here, that I'm showing in my map. I have plenty because we have run the whole script, but the land cover is value 15. If you expand the legend that we are using to plot this data, it's problem over here. And I'm going to change it to satellite over here just to have a nicer view. We can see this, the true color that, yeah. And see the outside. And now using the toolkit from Emil, I'm just going to easily create an RGB that is false color, calling it one of his functions here. So this is just have this information, but for the appropriate bands at the appropriate level, just to visualize it as a false color. And because we have run our whole script, that's already available here. So that same band color combination is available here, and this is how our EMIT data looks in a false color combination. Nice. Now we can apply the cloud mask. We saw this in Eric's tutorial. As you see here, the cloud mask in GE is included as a band over here. So I have to treat it as a band. And what we are going to do is just map, just extract that band and map it just to see what values it has. So this allows me to deal with the data, to interact with the data more easily. Over here. And with the inspector, I can see what values that mask has. So I see that where there is land, it has a value of 0. And what is the value of what has been masked, which is 1. The way Google Engine works with mask, you know that this is inverted. So I need to invert it because what is masked should be 0, and where I have data should be 1. So I can create a function very easily that use that mask that create a mask, but inverts that mask. So I can apply the mask to my data. We use a lot of like mask approach in Google Engine. So it even has a function, a built-in function called update mask. And every time that you applied an operation to an image in GE, whether you select a value, a band, or in this case applied a mask, you may lose the information, the date information. So this is very common when you are doing some operations. Just remember to add again the date of the data. Once you're working with multiple images, this becomes crucial because now you lose some key property of the information that you may need later on. So after we applied the mask, this is the result. We saw from Eric that he suggested actually a different quality product, the dilated cloud flag. We can change that easily here. Instead of using the cloud flag, let's use the dilated cloud flag. This is how it looks if we use the mask. We remove those pixels that had been masked as clouds. You see that there is still some residual over here. We can apply the buffer actually to the cloud mask to try to eliminate that residual of the cloud. But let's use this dilated cloud flag just to explore how it works. And I change it in the function, and over here I am applying it to the image. So it's going to be the 2.2. You can run it again. And let's see. This is the dilated one. I think it's too aggressive for this particular image. In this case, maybe I wouldn't use. I will stay with the cloud flag and try to remove other pixels. But it's up to you and to the user. But this is something to explore. So in this case, for this image, you saw that it was still a lot of residual. So the cloud flag, that mask wasn't that accurate. So what I did is just to create a buffer. It's not perfect, but it's something easy to apply it in Google Earth Engine. So I select the cloud flag and then I add additional pixels around the pixels that had been masked, about 100 meters. And this is the type of radius kernel that I'm using. And because everything has run already, this is the mask using the kernel, the buffer. It's not perfect. I still have the shadow. There is not a shadow one, but these are some things that you can do with this data, and it will be up to you how much you want to remove, what is your application, etc. So the next one is change the names of the bands. So to be something more intuitive, because now every time that I want to map this image on the map layer over here, I will need to be using the indices. And we have 285 bands. So it will be easier if I know the webland of each of those bands. So that's what I'm doing here. I read the information that it was in our properties at the image level. I read, these are the bands, these are the properties. Here are the weblands. I read this as a list and I apply it. I rename the bands based on that. I have to split this by the point. You see that there is a point here, and the bands, the name of the bands are given as strings, as text. So I'm only going to use the left part when we split this by the point. So just the first three numbers over here. And my new bands are going to start with SR, representing surface reflectance, underscore, and the webland. So once I have done that, it will be more intuitive to work with the data. This is what I do here. And now what we can do is to extract the spectra, something that we did also in the Jupyter notebook. this is the weight. I have the location. I'm keep working on that point that is over here. That is right here. And this is the function that is going to extract that information. It's not, and then I convert that to an array, to a list. So this is going to extract the pixel values for all the bands in that location. I transform it to an array so it's easy to plot, and then I use this to plot that, and that's what we can see here in this first chart over here. This is the missing spectra at that point. You can change this for another image, and you can also change this. You know that we have more than up to 900 nanometers, so we can change it to along this one. So this is where we don't have information. Like when we did in the Jupyter notebook was actually this was qualified as bad bands. We can put it there. And now let's explore the PACE data. So I know that we have some PACE image and calling directly an image from Emil's assets. And then using also his toolkit for visualization, I just call the parameters that he's using to visualize the data, and I map it over here, and it's 0.3. So this is the PACE image for that same area. It doesn't match exactly the date, but it is close. And something that we wanted to show here is the level of detail. Obviously, we are working with different spatial resolutions. PACE becomes very useful if you want to do national and regional and global scale type of analysis. It's great, excellent hyperspectral measurements, but given the nominal resolution of 1.2 kilometers, there are limiting things that you can do. For example, if I want to work at the plot level like this in this ag area, it is not that useful. And I think that many of you may already be acquainted with this reality when you are working with MODIS data or VSWIR data as compared to Landsat data. And I would like to highlight this because NASA, sometimes we are asked why do we need EMIT or something like that when we have PACE? And well, there are different things that we can do with the datasets that we have. Are complementary, but they are not exactly the same. So here I read the wetlands separate because PACE is not part of the collections that GE has. We are using images that Emil has transformed and uploaded to his asset space over here. If I want to give, we also have a number of bands with PACE data. It's about 122. And when we have this type of hyperspectral measurements, is needed to know the wetland that each band represents. This is not that crucial when you have 5, 10 bands, but when you have more than 100 bands, it is useful to apply indices, to calculate, to actually understand what you're looking at. You need to know what is the wetland that you are looking at. So I do something similar. I just rename the bands to something that is more intuitive based on the bands on the wetlands that the PACE data has available. And then we map that and also extract the data following the same process that we did for EMIT datasets. Because this is surface reflectance, also the values go from 0 to 1. And we can change this scale depending upon what dataset you are working with. Even when you're working with Landsat, we can change this scale. And then we plot it. And that's the graph that should show up here. And the reason why I originally had the EMIT data from 400 to 900 nanometers, it was just to have something that is comparable with the EMIT, with the PACE data as well, because it's from 3-something to 900 that we have hyperspectral measurements for PACE data, and then there are multispectral as compared with the EMIT that everything is hyperspectral for all the wavelengths. So I think it will be more fair to compare things that are more similar. So the range from 400 to 900 approximately is what compares more apples to apples over here. So that's what I'll go here. I'm just going to change this to 900. This is the same location because I am using the same point where we can extract that spectrum. And something that you can see here is that once you have plotted the data, you can open it in a window. You can download this as a CSV file, as an SVG, and use it for your other operations, next steps of how to work with the data. For the training a model and others. Obviously, you can select all the bands. It doesn't have to be only this. Obviously, the more bands, the better. And I think this is mostly what is this script. Then at the very end, we can also calculate the hyperspectral enable indices that we did in our notebook. Now that we know that we have a better name for the bands, both for PACE and for EMIT, we can select the bands that are used in these indices and apply an equation and calculate it. And that's already done. And we can see the results here. I'm plotting the ones that are for PACE, but commented are also the calculation using EMIT data. And if you want, we can uncomment this. Oops. Forward dash is for commenting here. But this is for the chlorophyll index red H. And this is the one for the carotenoid content index. And now that I uncommented the ones for EMIT, we can also calculate it for EMIT and compare. If you have many layers, as we have here, I have already set many to not show up automatically. If you click on 0, all of them will disappear, and then you just can only activate the ones that we care about. I calculate the EMIT, but I didn't map it. So let's map it. Add it, and that means add it to this map layer over here. So this is for our EMIT. Sorry. I'm using some palette that I'm calling as a requirement from Gina. Those are very neat. And let's change the name. EMIT. Let's run it again. I cannot see the... Oh, I forgot the T here. And I know you can explore this at your own pace. but the scripts are there to deal with the data. It's important to see how GE is reading these data sets and how you can explore them. So I'm going to remove everything, and let's see the carotenoid index from EMIT as compared to the one from PACE. I'm going to put the satellite database. You can see that for this plot of ag area, I just have few pixels. But if I see EMIT, I can see it at the plot level. That's very nice. So that's one example that we wanted to show you. And then how are we with time? No, I think that we are on time. So just at your own pace, check this park fire example. Emil uploaded some very useful information of PACE that coincides with the EMIT data, and you can just run that code there and see the spectra for pre and post fire for that location. But that's it. Thank you.
All right, thank you, Africa. There are a couple of questions in the Q&A, if you would like to take those really quickly.
Yeah, let me see.
So one of the questions is, what about the update mask?
Yeah, the update mask is used in the function that I created to apply to the image. If, for example, you want to process multiple EMIT images, which Google Engine is set up to do something like that, you create a function and then you apply that option to the image collection that has all the images that you want to work with.
Perfect. Thanks, Africa. The next question is, out of curiosity, does the cloud masking algorithm used in satellite-based hyperspectral images outperform FMask or other masking algorithms used in multispectral data?
And that's a good question. I think that will be something to explore. All these data sets are very new. But I have to say that I am surprised by the quality, not surprised, happy by the quality of the hyperspectral data that NASA is providing right now. And the atmospheric correction that is being applied is superior to whatever we were using in the past to have such high quality data.
Okay, thank you, Africa. There's actually a question that was also asked much earlier on from one of our webinar participants, and he was interested in indices for rock alterations.
That's not my area of expertise, but we can check. We are terrestrial land cover ecosystem.
Yes.
People. Yeah.
So we'll have to get back to this webinar participant offline. Let's see here. Let me jump to the chat. I think everyone has done a very good job responding to the questions. I had a temporary lap that I was disconnected for like 5 minutes. It was just spinning, but there were no interruptions to the webinar or any of the content. So that is wonderful. That's why I always have a co-host present. Just on my end, there have been a lot of questions about whether or not the recordings or in the slide decks and other content that's been presented in the last 2 days will be made available. Yes, yesterday's event was recorded. There is a little bit of post-processing that needs to take place. So, I will edit the recording for any, dead space at the beginning, our internal conversation, and also at the end, and add chapters to the recordings description so that our participants can navigate to that point within the recording that they would like to take a look at. And once all of that is done, we'll post the videos to a new YouTube channel. Many of you might be familiar with the NASA Earth Data YouTube account, which has been consolidated due to some agency efforts. And so I will send an email to all event registrants and participants, both from day one and from today, that will include links to the presentation repository, any additional links that our presenters would like me to pull out from that content, for example, Jupyter notebooks or anything you might think webinar registrants and participants would really benefit from. And also we'll include a link to the recordings. Okay, and so you can feel free to email me if you have any questions, if it has to do with the recordings. You can always feel free to email me, and if needed, I can forward your query to one of the subject matter experts from the science teams in the LWIR who were present during this 2-day event. So I don't have any further comments other than that, so I'm going to toss it back over to Africa to close us out.
Thank you so much, Jennifer. Thank you so much, everyone, for joining this webinar. I realized that oh no, I don't have the presentation here. Let me see if this works. Very briefly, just before we leave, it seems I can only share the screen. This is the first webinar that we have as a part of series that we are preparing. All the team that has joined in this webinar are working on an air action handbook that tries to bring multiple sensor data. And this webinar series is going to be part of that. This is the first one. So later on, we are going to have some more applied ones. The next one will be on snow and ice. Let me see if I can share. How to see that. I want to thank everyone, specifically everyone. Everyone has been great, but Eric and Masa, thank you so much. And Aya as well, all the presenters, but they have been with us through this journey to make this possible. And please check the webbook that contains all the information and even more for this webinar. We hope that to have those thematic ones later on. That's our goal. Thank you so much, everyone. And thank you so much, Jennifer, for everything. And I also realized that I had Masa's name wrong yesterday. So I also want to share to fix that right now. But thank you so much.